Hello, hello. Hey everyone. I just want to give a quick 5-minute warning that we'll be starting in about 5-ish, so you guys can come find your seats. Thanks.
All right, everyone, please take a seat. We're getting started. Please grab a seat. Aleo team, you're still standing over there. Everyone being very private in the back, please move to the seats. Adrian, take a seat. All right, welcome everyone to Privacy Evolution. This event is brought in together by the teams at Aleo, Anoma, Z Prize, and we have a wonderful sponsor for the after party later, which is Maven 11. First of all, a little bit of an introduction about myself. I am Awa. I am one of the co-founders of Anoma. In short bio, I used to work for surveillance capitalism, particularly in a company called Chainalysis. You might not know about Chainalysis, but don't worry, they know a lot about you. And now I work on Anoma, goods for the public. And I'll be emceeing you all day tonight. Cool. So just a recap of the logistics. In this country, nobody gives you water, but there is beer and wine for everyone. And if you have received the voucher at the beginning, you can swap it later on for pizza and some cocktails. So make sure you remember that. The talks go from 5 more or less until 10 p.m. and there will be breaks in between. There will be an after party from 10. And this event is live streamed. Ask the organizers for the link. And they will be taking some cool pics later on to upload as a souvenir. Important to remember, this is actually really important for the audience. After every talk and every panel, including fireside chats, we'll be opening up for questions and answers. The way this works is you have to raise your hand as high as you can, and then a mic will be airdropped to you by some autonomous organizations running the blockchain. So the program, you can take a look at it on the website, privacyevolution.paris. And yeah, help us spread the word about this event by including this hashtag in your tweets, Privacy Evolution. Cool. So with no longer ado, we'll get started with the talks. I'm actually giving the first one. All right, so I'm here to talk about privacy as a public good. First of all, I would like to recap on the state of privacy in Web3. So many of you know the most established protocols out there, they are pseudonymous. Pseudonymous means that all identities on your accounts are hidden behind this string of random characters. And at first look, at first glance, you actually can't tell really who's behind the usage of these accounts, right? But the issue is that actually whenever you interact with the blockchain and you make a transaction, it reveals a lot of data, particularly from the transaction graph. And this data can later on be all used to de-anonymize the accounts behind these pseudonyms. So this gives a lot of data for heuristic statistical analysis, and you can even correlate it with OSINT, so all the data you can find in the open web, from social media, from Google search, from the forums. Whenever you actually share your account publicly, that can be correlated to all these accounts with very trivial technology. And it's even easier if you use NFT in your as a Twitter profile. So what's important to mention here is that all this data is actually readable by everyone. And forget about the NSA, forget about the governments. Really, this data is readable by everyone, including anons in the internet. So, as Ian Maya said once, really the state of privacy in the current protocols is like Twitter, but for your bank account. Honestly, imagine that you have kind of like an amazing integration between your credit card, your bank account with Twitter, and then every time you make a payment with it, it just automatically tweets out, oh, this person has made this payment for this thing, right? And generally speaking, imagine that you have set up your credit card to pay for your Pornhub subscription. So every time you have to pay for the subscription, the Twitter goes out and says, hey, this person has paid for the subscription. So that's not great. The next level will be level 10. I would say is introduced by really cool cryptography, pioneered by Monero. So the intuition behind ring signatures is that basically 7 accounts, whenever there is a transaction to be signed, there are 7 random accounts, public keys that are picked from the entire pool. And then they are, so for the observer, so whoever is monitoring the chain, they cannot tell which one it was except for the person who signs. And this is theoretically actually not bad, as in theoretically you have a 1/7 chance to figure out who it is the one that actually signed. Except that if it's the case where you actually own like a big portion of all accounts in this network, right? And in that case, even if you're random sampling 7 accounts and one of them was signed, imagine that you actually were the one that owned 6 out of 7. In that case, the privacy is not really good. So now we have next level, which is over 9,999 with ZK snarks. So it was pioneered by the Zero protocol, the Zero Cash protocol, and it was deployed for the first time in the protocol called Zcash. Zcash leverages the knowledge proofs for all ZK snarks, and what it enables is shielded transactions. So instead of having transparent transactions that reveal an entire transaction graph, what you have here is that all the information that is involved in that part gets completely hidden. So that will make it much, much harder, actually mathematically impossible to de-anonymize Zcash. And I've been thinking that so far at Web3, we have been thinking about privacy as kind of like a lot as a feature, as an add-on. And what if we're thinking and designing privacy more as a public good? So what makes a public good a public good? And the first property is that it is anti-rivalrous. Basically, the more people use it, the better privacy for everyone. The other property is that it has to be non-excludable. We have to design the systems in a way that nobody is able to prevent anyone from accessing to it, not even the governments. And yeah, if you look at the current state of privacy and the current state of evolution of protocols, it is evolving. And we're working on one protocol. It's just one among many others, and many other teams here you can talk about what it is that they're working on. That is called Namada. Namada provides Zcash-like privacy, but for any assets. And it deploys an upgrade of the sapling circuit of Zcash that allows all assets to share one anonymity set, which is a really important property, especially if you want to, for example, undox your NFTs on Ethereum. You can all send them to Namada, and then in Namada, they will all be sharing NFTs, will be sharing the same anonymity set as fungible assets and any others. So it will look completely indistinguishable from even a transfer of the native token, or many other NFTs, or many other assets from Cosmos or Ethereum. So how does Namada as a project experiment with turning privacy as a public good? And the goal here is that the more assets there are and activity there is in the shielded pool, leads to more stronger privacy, not only for you, the one who's using the shielded pool, but for everyone else too. So given that goal, what we can do is we can configure protocol incentives and create incentive mechanisms to basically incentivize the shielded pool usage. And this is something really cool about Namada, where you can, as a user, actually, you might not care for yourself about using private transfers or shielded transfers, but if you actually use shielded transfers, you're not only contributing to the anonymity set, but you're also earning protocol incentives based on that. So you can basically earn by using privacy. So, but there's more, right, to come? Like, privacy keeps evolving. We're not there yet. And another project that we're working on is Anoma. Anoma is a novel architecture, and it is a unified architecture that enables you to build fully decentralized applications, so fully end-to-end. And the architecture is characterized for being intent-centric, among other properties. But what's coolest about Anoma is that it comes with a unified execution environment for the apps. And this execution environment is able to handle 3 different levels of privacy: fully transparent, shielded, or private, which might be something really interesting if you want to build applications that are not necessarily fully transparent or fully shielded, but that actually benefit from a mix of that simultaneously. And I would like to remind all of us again about the purpose and the ethos of this entire space. There is a class of problems that can be defined as those flaws or those inefficiencies in the protocol design, in the design of economics of all these applications, all this infrastructure that we build, that basically allows a few to extract the disproportional amount of value from the users without adding nearly closely the amount of value in the process, right? There's this entire class of things. And in the entire space, we speak a lot about MEV, like from running, minor extractable value, etc. But honestly, surveillance capitalism is nothing different than that. It's like it gives the ability to the few, corporations, governments, to other parties, to extract a lot of value from the users without really adding any value in the process. And if that exists, that needs to be eliminated. We need to continue iterating so we eliminate that possibility, so we change the economics. So in the end, we reach a state where the relationship between the user and the systems that we're building are more equitable. So yeah, what are you guys doing? Are you currently working on Web 2? Are you thinking of joining Web 2? So I look at Web 2 as like, this is medieval tech, honestly, guys. And you could be joining Web 3 and joining all these things here and build godlike technology. So the choice is yours. Actually, I have time for questions, if anyone has any. I need a mic for Joshua.
What's the difference between shielded and private?
You should tell me about it. So the difference between shielded and private is something that is a distinction that matters in architecture particularly. So in the case of Anoma architecture, it is intent-centric. So the basic unit is user intents, and if we leverage zero-knowledge proofs to enable privacy, it has this constraint that the who of the intent is kept fully shielded, fully private, but the what needs to be kept transparent so decentralized solvers can actually do the compute and find matching intents. But with fully private intents, which is something that, and by the way, with shielding, actually that is by now the best privacy guarantees you can get if you're building applications that need counterparty discovery and they're interactive. But if you want to keep everything fully private, so the intent and every interaction is fully encrypted, you can leverage really cool cryptography called fully homomorphic encryption. And that is what will allow us to achieve like fully private state.
What is the timeline for Namada? When can we expect to use it?
The timeline for Namada. So the first thing you should do is take a look at the announcements on Twitter. Namada should be coming up so we're doing a trusted setup ceremony. And that one we're planning to release sometime this summer, if not early fall. And that will be paired with incentivized testnets, public testnets. So I think with that you can like basically try the entire stack. Well, even integrate it with like end user wallets that allow you to, it's multi-asset. It's like, this is really cool. Some of my team members actually doing a demo about this. But this is actually the very first multi-asset wallet that's interoperable, but that also allows you to send shielded transactions as well as transparent ones for any assets that you bridge into Anoma.
Question regarding the Namada chain. Well, the ecosystem, who is running these nodes? Is it you?
No, Namada uses proof of stake as a civil resistance mechanism. So it is, I think you will need one NAM token in order to start operating a node. But then it will follow the same rules as, it's very similar to, for example, Cosmos proof of stake, economically speaking. So it is a permissionless system.
Okay.
Cool. I think we'll be moving on to the next talk. Thank you. Next up, we have Vivian Ford, the head of community at Aleo, and Vivian will be given a talk about who actually cares about privacy.
Cool. Sorry. Hi, everyone. Good to see a pretty crowded room. I'm here to talk about privacy and why you should bother. And maybe you guys already bother because you're here, but I used to not bother. And then I realized you kind of have to. So right now, we exist in a world where there's a big trade-off between convenience and privacy, right? So if you were to choose convenience over privacy, which I'm sure many of you do on a daily basis, that might look like accepting a terms and conditions without reading it. Which, did you know that in 2019, they did a study, and 9% of people read the full terms and conditions, which is shockingly high, right? But apparently those people care. So convenience over privacy, it's not even that easy to really choose convenience over privacy, because when you look at a company like Spotify, all right, let's say you want to listen to a really great song, and you read Spotify's terms and conditions, and you go to Apple Music's terms and conditions, and you go to YouTube's terms and conditions, and it's such a pain to go through for you to research each individual terms and conditions, and it actually ends up being somewhat of a monopoly. What if you were to choose privacy over convenience? Well, there is kind of a world that we do this every day, traditional banking. You want to bank with Chase, you go to Chase, you open an account. They're pretty strict about no one else knowing the contents of what's inside your account. You can't find out your neighbor Sally's net worth by going to her bank and just asking. But it's also super inconvenient because you're dealing with Chase's bank holidays and weekends, and wires take 7 to 10 days with a $10 fee and $25 for international, right? I don't work at Chase. So, current state of privacy, pretty inconsistent trade-off. I don't know if you guys know VentureBeat, but that's a media publication, and this popped up. Oh, you can't really read it. That's okay. This popped up when I was trying to read an article, and they basically just say manage your privacy, what they use the data for, and they just have functional analytics, advertising, 3 separate pinpoints that you don't really know what that means. Web3, though, in practice, as we saw, is pretty pseudo-anonymous, right? The thing is, Web 2 at the start wasn't where it is now. When Facebook and Gmail and all these companies started, privacy wasn't the good that it soon became. So what does it mean for a future state of privacy? Well, privacy by default and convenient by default, especially with more and more of our interactions becoming digital nowadays. It's super important to actually have a way that you can control what data you want shared and what data you don't want shared. Think of it if you were to go to that same bank and ask Chase for a loan, and nowadays Chase can take all of your information and they can sell it to lenders and insurance companies and whoever they want. But wouldn't it be nice if you could go without sharing any information about your bank, how much money you have, or anything of that sort, and only have information on the loan? So there's clearly a need for this, but it's also a kind of complicated need. Slapping privacy on top of something that is inherently public is not the most elegant solution, like a ZK rollup. And for a hardware security module, you have to inherently trust that the module will not be compromised. At Aleo, we're building an L1 blockchain that is focused inherently private by default. And much of the computation is done off-chain in a zero-knowledge proof. So, what will ZK proofs necessarily do for you? Well, that's a question you gotta find out for yourself. But there's an individual impact, and then there's a more global impact. On the individual impact, let's take something as simple as going to a bar and showing your ID and trying to get a drink, which in America is the ripe old age of 21. So you go to a bar, you show your ID, and sometimes they swipe it, and they have all of this information on you that maybe you didn't want to share, because maybe you grew up on a really embarrassing street, and you don't want people to know, but now everybody knows. So wouldn't it be great to be able to just go to a bar, share information, and the only information that they see is that, yes, you are indeed of the legal drinking age. Another big impact is voting. We've seen, especially in the last few years, a lot of issues with the voting system. Wouldn't it be nice if you could go to a location and maybe there was a physical device, and maybe that physical device, when you voted for whoever you vote for, would give you would present a zero knowledge proof. You would have a proof, and that would be unique to you, so you would have a different proof than the person in front of you, behind you. And at the end, all of the votes that were counted would be displayed by these proofs online or wherever, and you could search to ensure that the person you voted for was indeed, or that your vote was indeed counted and was not tampered with. So inherently, trust and identity go hand in hand, right? If I have a secret, I want to know who you are before I tell you this secret, and I want to know a little bit about you to make sure that I can tell that I can trust you. Zero-knowledge proofs are essentially changing the nature of trust. We're not asking people to stop trusting, we're just having people change what they put their trust in, so they no longer put their trust in systems or people. So start paying attention, because it's going to move fast. And in order to save a bit of time, I think we'll just move to the next speaker. That works?
All right, next one is a fireside chat with Olaf.
Hey, thank you very much. Happy to be here.
Then next we have Howard from Aleo
Hi.
and Adrian.
All right.
Okay, the stage is all yours.
Amazing. Thanks, everyone, for being here. Very excited for this conversation on zero-knowledge proofs and their applications in blockchains. So I think one question that is sort of interesting as a way to kick things off is, why haven't zero-knowledge proofs been used in the past? Like, why now? Why wasn't Bitcoin built with this, built in? And I'm curious your guys' perspective on that.
Yeah, it's hard. This is really the easy answer. And this is why I'm incredibly grateful to Zcash and the Electric Coin Company, because honestly, when Zcash pioneered this entire space, and without Zcash, we wouldn't be here, because practically speaking, like, zero-knowledge proofs got really good last year, and I think we're just sort of at the beginning of this exponential rise of what the technology can do. But yeah, the easy answer is it's very hard.
I'll give a quick historical take on it.
Are looking at zero-knowledge proofs as a way to scale blockchains. I'm curious, how do you guys think about any trade-offs between privacy and scalability? Or is one of these going to end up being significantly more useful in blockchains than the other? Hard to predict, but I feel like I never thought of it as a scalability solution for years, and now I do.
Yeah, I mean, from my side, I'm personally not convinced that the scalability debate is going to be all that relevant in the next couple of years. Mostly because we've been mostly thinking about scalability in the sense of scalability within a single security model, and that's very difficult. But I think practically speaking, scaling happens horizontally. So we have many different security models and like many different chains running at the same time. I am much more excited about the application of ZKPs for privacy, because they provide something completely new to end users, like where we can now build systems, like we can build private cache, like private asset agnostic cache, something that I was talking about with Namada, right? And this is, to me, way more exciting, because I think end users will end up caring much more about privacy than they care about scalability. So I'm personally much more bullish on ZKPs for privacy than for scalability. Yeah.
I would lead with one example in order to try to motivate the privacy discussion, which is that, like, if I want to send money to you today, and like you give me your bank account number, knowing your bank account number reveals nothing about you. Like, I don't know how much money you have in the bank, where you work and how much money you make there, where you go spend your money. Like, I don't know any of these things, right? But if you gave me your Ethereum address and I send you USDC, like, I would learn everything about you from then on, because I can not only know your history, but I can track you for the rest of the time. And like, if you're married and you want to even just buy like an anniversary gift for your spouse, and assuming you guys are close and you share finances, you probably know each other's wallets. I can just look up like how much did you spend? Where did you go buy this gift from? And when did you remember that our anniversary is coming up? And so, like, these are the kind of weird things about like the human kind of relationships that we have when you don't have privacy. And so from that perspective, I think what ZKPs enable, especially in a Web3 context, is really getting you to this dimension where you kind of have these social interactions where you assume there is, like, maybe to put a bad image in your mind, but like in the restroom that you have stalls. Like imagine going to the bathroom without stalls. Like that's kind of what it feels like when you use Web3 on some platforms today. But I think at the net of it, on the scaling question, to answer that, like I think that the scaling tech that we have today, especially with ZKPs, is incredibly cool. I think one of the big challenges is that it potentially might even worsen the privacy argument. And the reason I say that is that, and this might be controversial, is in order to do like these roll-ups that you've seen, these giant batch computations, you need a central processor who actually takes and ingests everybody's state into one place at one time in order to produce these large, massive, crazy, cool statements. And a huge part of that is that you need to get the information sharing on that right. And so, like, functionally speaking today, there isn't a lot of ZK being used for privacy in that domain. And I think that it's important for those who are especially trying to batch aggregate and increase throughput to think about it from like the quote unquote ZK rollup lens. I think that will give a far better guarantee for users. And I think that's an area that people should frankly dive deeper into.
Yeah, and I almost feel like crypto users today almost have like Stockholm syndrome about privacy. Like we just assume that everything is public because it's always been that way, and we're super used to it. It's like, oh, let's monitor what this address is doing, and we're like really so used to it that I think people have almost forgotten that it's really screwed up. And in reality, in like normal business context, normal personal life, like nobody can see, nor should they really be able to see, like everything you're doing and your whole history and everything. So it's this odd thing where I feel like we've gotten so used to it in crypto that people have almost like forgotten that it's very bizarre.
I think this is shifting actually, because until recently, we've all lived in this magic world where there were no real world implications. I mean, people did lots of trading and maybe they wanted to hide some money from the tax authorities, but that was like the majority of use cases. But now, like if you're actually thinking these systems get adopted for payments, we start having this problem like what the US is now having with abortion data, right? And the period tracking apps. And all of a sudden, like things that where you were maybe fine sharing this data 5 years ago, all of a sudden become illegal. And on a blockchain, you have a permanent record. Like you should think of Ethereum and your Ethereum addresses that you've shared with anyone in the world as like your permanent record. This will exist for eternity. And you've better be goddamn sure that the things you've done will never be illegal going forward, even if they were legal when you did them. Because people will get prosecuted for this. And this is, I think, something that's slowly starting to dawn on people as sort of centralized institutions around us start failing, that like privacy guarantees are incredibly important, while the world around you is sort of slowly dissolving.
Yeah, and I think this is another interesting, trade-off with privacy is there's often a need for like what I might describe as composability with privacy. Yeah. So, suppose you have a big a data related to your company. Let's say it's Polychain's fund or something. I might have to disclose certain parts of that data to one group and certain parts to another group, but I might not want to share the history of everything we've ever done with everyone when I have to disclose. How are Aleo and Anoma thinking about this sort of composable privacy and the ability to share certain components of a data set with one party, but not the whole thing?
I think one way that, at least in the Aleo architecture, we've been very cognizant about is the concept of view keys. In our architecture, basically, like the data has a long chain of history in terms of how it's born and its provenance and its existence. So there's view keys for transactions, there's view keys for your records in those transactions, there's view keys for your account, there's view keys everywhere basically. And I think that at least has been one aspect that, in our particular case, that the ZKPs that we develop are actually verifying the encryption that's going on when it gets posted, so that it's clearly attested against the key that we're using there. In terms of other aspects that I think we could do better on, though, frankly, is that like the selective disclosure kind of concepts, I think, could be formalized into protocols that applications build on a system like this. And I think that's an area that frankly is currently lacking or missing a lot of good UI UX, because when you have multi-parties, like you have a third-party auditor, you have your internal accounting firms, you have also the actual managers, say in this case of a fund, that different parties need access to different granularity of data, and sometimes you also may need to revoke access to that afterwards. This is something that I think a lot of these types of ZK applications have not thought deeply about yet, in part because it's a hard problem. But I think that's an area that is at the moment probably unexplored, at least to my knowledge. But maybe Anoma has worked on this.
So we are roughly doing exactly the same thing, which is you've got to, when you design your circuits, you should think about viewing keys and how individuals can reveal data. I mean, again, Sapling did this for Zcash, where they introduced the idea of a viewing key, which is not only useful if you want to reveal data to, let's say, the tax authorities or an auditing firm for a fund, but also when you want to do things like you have a mobile wallet and you want your transaction history to be shown to you, but you want to have a proper block explorer. If you can upload the viewing key from your mobile wallet to your browser can display your entire transaction history. And if you don't have these kinds of optional viewing keys, you can't do this. You can, then you always need to ship the private keys that actually have spend authority around. And so I think incredibly granular and generalized viewing keys while doing the circuit design is like an absolute key. And I think we haven't scratched we've just started scratching the surface. It's, because there's like one circuit that has them, that's actually in use at the moment.
And God, I hope it does not leak.
Oh yeah.
But maybe just for those in the audience to understand from a high level, it's probably also worth noting. So the architecture that you can assume is normally when you have like a Bitcoin or Ethereum private key goes straight to address. In these models, the way it typically works is you go private key to view key, then view key derives your address. That's the rough architecture there. Depending on the schema, it might be a little different, but on a high level intuition is that it all roots from your private key, and everything kind of extends out from there.
And so, I think the conversation around zero-knowledge proofs, some of these use cases are really, really obvious. Like, we all know about it. It's like transactional privacy, voting privacy, like if you're voting in a DAO, like have it be private. Are there any sort of less obvious or more counterintuitive applications that you or your teams have thought of? Or are you guys mostly focused on these kind of core financial privacy for existing blockchain use cases?
So there are some for which there aren't any circuits yet. So for example, private auctions, private batch auctions. The thing is you need not only ZKPs, but you also need a distributed key generation protocol that you can do batch decryption with. And then you can start aggregating a bunch of privacy-preserving votes that are all encrypted until, let's say, for 2 weeks. And then after 2 weeks, they're decrypted as a batch. And this is sort of you tallying. So if everyone submits private votes to this election ballot box, and then after 2 weeks, they open the ballot box and they do the counting, and then it's publicly verifiable. I think a lot of the more complex applications so one of the big problems in ZKPs is that doing things over shared state is very difficult. Like the person that generates the proof needs to have access to all the state, which means someone has to know all the state. So I was saying this earlier that if the best we can currently do if you want interactivity, if you want to have multiple parties, the what is public and the who is private. Once we get to fully homomorphic encryption in a couple of years, that it's fast enough, we can ideally do things over shared private state, where we do homomorphically encrypted private state that we then generate ZKPs over. And I think a lot of the very complex use cases will require this, but that's 5-10 years down the line.
I think just to add on to that, the homomorphic encryption thing couldn't be emphasized enough, that in order to get you to a universe where the computations, for the logic itself is fully private, you really need this type of primitives in order to make it actually work end to end. And one of the examples that in terms of applications that I think a lot of people have talked about, but I've yet to actually see a good implementation of, is basically just like a good Uniswap that's ZK based. The MEV problem fundamentally is a big deal, and it's cool to see, especially in the ETH community, so many people trying to design systems where you price in the risk on that front and you create auctions out of it. But I think that there's frankly, like when you can selectively hide what data you want to show, you can create these types of trading games out of it that I think are fundamentally far richer than we could even imagine. Like today, the New York Stock Exchange gives you one concept of privacy and selective disclosure in the sense that different firms can opt in to pay for licenses to get access to L2 order books, L3, L4, et cetera. But that's like just one way to slice and dice information. And separately, in terms of how that data is cleared and how it's settled, it's also very much just one variant of it. But people haven't tried exploring the different facets and the game theoretic optimizations you could do when, say, maybe I can only see volume, or I can only see last trades, or I can see how much is going to be traded, but I don't know who, et cetera. And you can start playing these kind of games where different people play in this ecosystem to kind of serve a different role. And frankly, like this then says like MEV might not be non-zero, but it says that different parties are incentivized based on the MEV that they get. And I think that there's a universe of applications there that just hasn't been deeply looked into at the moment.
I would say though, on the MEV front, MEV is very solvable even right now if you're willing to re-architect blockchains sort of from first principles. So we've been working on a protocol called Fervio, which is a distributed key generation protocol where the validator set maintains a public key and all transactions are encrypted against the public key. And then on the next block, they're decrypted, where you can't reestablish the ordering of those transactions, which mitigates a lot of MEV. Because you can't do sandwich attacks, you can't do front-running attacks, you can't do back-running attacks, even if because you have finality. So we don't need fancy fully homomorphic encryption to solve MEV, but I agree.
I think also you should correct me if I'm wrong on this, but I think one of the trade-offs, at least that I have seen from some of the experiences on developing the MEV-free systems, is like you're usually trading off kind of throughput against the optionality of MEV, because you might need to commit and reveal, or you might need to do multi steps, might need multiple block confirmations. But
yeah, so I wouldn't say throughput, I'd say latency.
That's a good way.
So I mean, like for example, Fervio is not commit reveal, so you don't have the problems that it's an economic game where someone may choose not to reveal, but you do have the extra latency because in the best case, the transactions get executed only one block later.
That's pretty cool.
You should adopt it. It's
I'm
open source.
I'm interested. We should chat.
And this kind of MEV, it's interesting when you frame it as just like information that's revealed to the market. One of the classic problems of like big block trades is that you have to go to OTC desks, and these OTC desks all talk to each other. And if you want to buy, $100 million of Bitcoin in one go, like you don't go to the OTC desk and say, I want 100 million of Bitcoin. You go to 10 OTC desks and say, I want 10 million each, but then like they all chatter and you kind of get front run, right? There's all this class of problems that aren't even unique to crypto that are a sort of MEV. I mean, it's obviously different than sandwich attacks, but it's conceptually the same. It's like information is being leaked about the future, and I'm going to act on that ahead of time. So I feel like there's this class of applications that apply not just to problems in public crypto blockchains, but also like just finance.
Absolutely. Like I like to think of what is MEV as it's when you do an action, before this action is actually settled, someone else sees this and can front run you, right? Like Robinhood does the same thing where they sell order flow to Citadel. It's like someone has a game theoretical advantage over ordinary users when they submit intentions or actions that they want to have settled. I mean, I didn't realize this was also the case for OTC Desk, but yeah, it makes sense.
Yeah, I mean, Robinhood's business model, in a sense, is selling MEV.
Yeah.
They sell MEV to, Citadel or Jump, who actually executes the MEV, and they're like a broker for MEV. I mean, it's a different way of framing it, but it is funny to look at the crypto lens through kind of trad finance and see that a lot of the same problems are out there.
I think trad finance should be very afraid that like crypto is like making a bunch of things like way better, both on the privacy side, on the MEV side, also on like simply accessibility side, where you can have like multi-chain atomic settlement. Like you can imagine you can have systems where it's like the New York Stock Exchange and the London Stock Exchange, you can do like atomic settlement between two of them. I think TradFi is going to get a little bit slaughtered here.
Yeah, I couldn't agree more. So one question that's a little bit more future-looking is how far are we away from what I might call like a privacy-preserving virtual machine? That is like a VM that can execute computation on encrypted data. Is this like, yeah, how far away is that in your estimation, and what do we need to get there?
I'm biased here, so I'll put a caveat on it. But there is a developer workshop we're doing tomorrow where I think I'm showcasing this. But I guess the definition of it is also very, very much open up in the air. I think like in terms of the richness of what you can do in a VM, that's really the question. Because today, like, can you do it? I actually think we probably could all already start doing it, but the challenge is that it's not going to be very fast. Relative to just doing a normal computation without the privacy bits and the ZK bits, it's very slow, relatively speaking. So I think that that's probably the big trade-off here. And then in terms of getting it fast, I think given how exponential things have been going, it might be just a matter of a year or two away, I think, just personally speaking.
Yeah, I concur. I think we're starting to see the sort of first attempts this year, next year, and I think they're going to be very basic to begin with, simply because provers, for example, are still relatively slow for if you want to generalize compute. But then in the next 2-3 years, this is going to get incredibly good. And I mean, like, if we follow this exponential growth curve, ZKPs are going to be mind-blowing in 3 years from now.
Yeah, so open source Google search engine in 3 years.
Your grandmother's going to be using ZKPs in 3 years. I'm kidding.
So Google may require FHE. That may be slightly further out.
Okay. So to think again about sort of the merits of privacy, one thing I think about a lot as an investor is when is privacy a need versus when is it kind of a want? So I think a lot of times there's like a wake-up call that turns it from a want to a need. But a lot of people, for example, use Signal, which is end-to-end encrypted, as opposed to, say, iMessage or something like that. And I'm curious, like, how do you guys think about the market for, okay, we like need this today in order to function, and like the size of that suite of applications versus sort of the consumer choice, like I opt into privacy, but it's not like I use Signal because I'm a drug dealer. I just use Signal because I want privacy for my everyday communications. Because as an investor, I think it's an interesting question. It's like, what are the respective sizes of those two markets?
I mean, Signal clearly had their moment with the Snowden files. This was sort of when the public eye started to realize how bad a lot of the digital communication security currently is. And I think privacy, financial privacy, may have had this, or blockchain-based privacy may have had this moment this year with the abortion debate in the States. Because all of a sudden, I think people are starting to realize that, like, you generate a ton of very critical metadata that currently is fully transparent. And so I would expect that we probably start seeing the shift now where a lot more people are going to start demanding privacy-preserving apps before they start using, get really deep into the tech and want to ingrain this tech into their everyday life. Like, I would even argue my parents will probably never use a transparent blockchain. Like, the first time they'll use a blockchain is going to be a privacy-preserving payment system.
I think one of the challenges with adoption for privacy is that people look at privacy from a defense perspective, in the sense that I'm protecting my assets, or I'm protecting my data, I'm protecting my information. I think that one of the strongest catalysts that will get us to a universe where it's kind of the default is when we utilize the features of privacy to enable applications that, frankly, today, like, don't exist, or we just don't know how to do yet. And what I mean by that is, like, just taking the bank account example for a moment. Like, in Web 2, like, you don't really think about the feature of privacy necessarily when you sign into your bank account. It's just assumed that it's there, if that makes sense, because the application needs it. I think that in the Web 3 context, there's going to be a host of these types of applications where you're not actively thinking about the privacy, but it's implicitly there because it needs to be there for this thing to function. So, like, for example, when you're thinking about gaming and you want to do a game like Battleship, you don't really think, is the other player's board hidden from me? Like, can I see your ship? It's just a part of the game. It has to be, right? So, like, when you think about it like that, like, I think that it ends up being kind of implicitly adopted. And when people start building applications that require this relationship where different peers can interact directly and transparently, but they can't see each other's information necessarily, it will naturally and kind of as a byproduct become adopted.
I think it's really important to understand, and I think a lot of people in the traditional world don't realize this, because sort of the narrative has always been you can use blockchains for criminal activity. that like Web 2 offers significantly stronger privacy guarantees than anything currently in Web 3. Like, as you said, your bank account in Web 2 is natively private. Maybe not to everyone, but at least to the majority of people. The same is true for like social media. Most of the data is private. It's at least private to the world. It's not private to certain companies. But like the way we adopted Web 3 is sort of weakened everyone's privacy guarantees very significantly. And I think sort of this year, next year, we're going to start seeing a massive shift backwards where we go like, we shouldn't be worse than existing systems.
Yeah, I also think there's a generational effect where the younger generation simultaneously feels more comfortable sharing more data online and is aware of like that they're doing that. I feel like the older generation was like you're not as comfortable sharing data online, but also didn't realize like the products they were using and how they worked, and you're the customer if you don't pay, etc. I feel like the younger generation knows that, and they sort of participate anyway, but they're at least aware of it. And so just as there's this kind of generational shift, I think there's going to be more and more need for, or more and more desire for privacy in these applications. An interesting, like early use case that I would describe as maybe not obvious is a game like, for example, Dark Forest, that uses ZKPs in a gaming context. I'm curious if you think there's going to be like a suite. Is there like a suite of gaming applications that is going to come out of ZKPs?
Yes.
Yeah. I would say casinos, poker. Like poker is honestly one of the very first obvious applications because it's like a simple enough game that's like not super hard to do in their knowledge, but it's something that has become significantly worse over the years due to sort of the regulatory force on the Web 2 companies. So yeah, I'm pretty excited. I think in the next year we'll see like a very good decentralized poker game.
I don't want to show too much on this dev workshop, but we're going to show roulette in this particular case, full end-to-end, spinning wheel, everything. I think the thing that's going to get very good and very, very popular very quickly for people who like to play these types of games online is the ability to actually know that the randomness is truly random and it was computed using a specific function, so that it's not gameable. That I think is the big kind of crux there in terms of online gambling. That like it hasn't existed in the past. You always have to trust the house, and there's no way to publicly verify it. There's been talks that certainly like Chainlink has developed the VRF stuff, but in practice, from my own surveys, like the challenge is that it's usually either too gas expensive or too slow to actually deploy on decentralized systems today. So like this is where I think like when you get into the ZK context, frankly, it gets really really good really fast.
Yeah, and this is kind of a weird way to frame it, but if you're a rational gambler, in which is again maybe a little bit of an oxymoron, but suppose you're actually trying to get the best odds possible yet still gamble, it feels like the cost of like running a physical casino, for example, is pretty massive, and it means that those casinos need to have a bigger edge in the games they offer. Once this is sort of online and open access, it's going to be a lot easier to deploy games that have a much, much smaller house edge. And, therefore, again, if you assume rational gamblers do exist somehow, I would rather play the online blockchain slot machine than the one at the Win because I'm actually getting way better odds. So there's like a business model element here too, which is if you do believe that people are going to play where they think they're going to win more, on average, I think the overhead to run these sort of decentralized online casinos is way lower than a physical casino.
Couldn't agree more.
So to shift gears a little bit, you guys both have a domain-specific language that I'm gonna shell the dev workshop now.
Thanks.
But you guys both have a domain-specific language for programmers to interact with your systems. How did you think about making that just a high-level decision to make a domain-specific language? And how do you think about that being either accelerating an accelerant sort of to adoption, or something that will slow down adoption but be better architecture in the long run? Sort of how did you think through those decisions?
First off, they have this IR called Vampire. It's very cool. It's like a polynomially represented structure. It's great. But I guess like to give a high level context, I think at least like some of the challenges that I think we probably have both faced is one is performance is like one of the biggest challenges in terms of just expressing things, because when you like hand wire circuits and like when I've kind of been writing ZK circuits for, what is it now, like 7 years. Like the problem back in the day was there's no tooling or infrastructure. You just literally mathematically write it out, and then you write it in C code, and you just hope that it matches. And when it errors, you like literally have to go like trace line by line again, or like if something overflows, you have to like GDB the thing and like try to find it. It was really bad. So but the problem the challenge is that like it's super fast that when you do it that way, because you're like literally getting down to the wires in order to calculate it. So the trade-off is always performance versus usability, I think is one of the big principles here. Like the more you abstract, the more cost you implicitly introduce, right? And so you're trying to like minimize that as you're going higher and higher, so that people who don't know ZK or maybe are just beginner coders actually can humanely write in a DSL here, in a language basically. So I think that's one aspect that, you know, we've certainly taken different approaches on, to my knowledge, that, you know, in our case, because we've stuck with R1CS, there isn't much of a polynomial representation we can do. We ended up basically devising specialized circuits for opcodes that we think are highly useful, and then saying for people, hey, with these opcodes, you know what opcodes are. Like, you can write assembly possibly, and if not, at least there are PL people who can write higher level languages that compile to opcodes. Then from there, like, you can take this as a primitive and kind of run with it. But yeah, you should talk about your approach. It's very cool.
Yeah, so Vampire is, like if you come from compilers, it's maybe kind of similar to LLVM. It's an intermediate representation that can have many different backends. So you can write a circuit in Vampire, you can then say, I want to like target Halo 2, I want to target a Stark, I want to target Groth 16. This is sort of like quite nice that it's backend agnostic. But this is sort of the first step in this journey, which is like, instead of having to hand write circuits, you can write now polynomials in the DSL in Vampire. But over time, we'll actually probably get sort of high-level languages over this IR. Something like Juvix will eventually compile to Vampire, compile to circuits. And at that point, you just have a completely normal programming language that you can use to write circuits. I think this is critical also for adoption, because we want to give like non-cryptographers the ability to safely write circuits in order to really give these tools so that we can have way more privacy-preserving applications over time. Because currently it's incredibly hard. Like there's probably less than, I don't know, 30 people in the world that are competent at writing circuits. And this has to change. But this would have been the same in like the early computer days if everyone had to write effectively assembly in order to write a video game, right?
I would also add, just kind of more taking a step back, broadly speaking, as an industry, one of the challenges that at least I feel like is growing right now is like there's snarks, there's starks, there's plonks, there's bulletproofs, and even within like plonks, there's like 20 different types of plonks. And one of the big challenges is that in order to allow these proof systems to all kind of actually communicate with each other, you need some common representation or format that can actually get you between the different domains, so that one, you could even just benchmark the performance of a design across them. But then two, like say I want to like move something from I don't know, Anoma to Aleo to Polygon to StarkNet, whatever. Like there's no humane way to do interop at the moment. And so that's why I think like things like Vampire, where you can like potentially easily just move from one domain to another domain, even if it's not the most efficient translation, as long as you can translate it and then check it very quickly, so you don't have to re-architect another protocol stack from the ground up. I think that's a very big deal. Like there is no common formats to interchange at the moment.
And I mean, in the beginning, this will always be that maybe you have to hand optimize it. Like, so you use Vampire, and then you get an output, and then you start hand optimizing it if it's performance critical. But over time, this will get, just like the tooling will get better, and just like no one is writing assembly nowadays, the tooling to go from sort of Vampire to an actual proving system and an actual circuit will just get better, and a lot of the optimizations will just get baked into the compiler stack.
And from sort of like a go-to-market perspective, in a sense, Anoma and Aleo are both, day one sort of products for developers. How have you and your teams, spent time making sure that, once this is launched and out of the box and ready to go, that people will be able to meaningfully interact with it? Because I feel like this is something that in crypto development is often sort of understated, is how much work is required in order to not just launch sort of a proof of concept protocol, but actually have it be such that a sort of, quote, regular developer, again, relatively speaking, can sort of come in and tinker with it out of the box and deploy something on top of it. How have you guys been approaching that?
I think one of the things that I can tell you guys have thought a lot about, and we certainly think a ton about as well, is just the need to have a full stack interface. Like, if you don't have a full stack, the user journey isn't complete. And the problem for developers is you'll get started here, you'll miss a step there, but you can see that there's another step that'll work if you can just get there, but you don't know how. I think focusing on tooling and infrastructure that gets you broadly there is one aspect. I think another aspect that is often overlooked in the ZK domain, and generally in the crypto domain, is that, like, in the ZK programming model, like, we're fundamentally changing how programs are executed. Like, for ETH developers coming in, they have this kind of, and I'm an ETH developer too, it's like, you have this mindset where everything lives on chain, and like when you want to like do an execution, you just send a transaction and they'll run it for you, right? But like in this new universe, like you might run it yourself, or a third party might run it, but a lot of this is happening off chain, and like if you're executing off chain, like the state may or may not be available for you on chain. You might only have part of the state available on chain. You might have some off chain too, and it has to be managed somewhere. And for engineers, like they have to actually keep a track of this state. And so there's just a lot more data that's going through. And I think when you add on the fact that people want to do scalability with it, so you're going to ingest a lot more people's data and a lot more state at the same time, you end up with this crazy complexity factor that just grows far bigger than what a traditional Ethereum dApp might look like. And so I think that's where it's critical to support good tooling, good infrastructure, and frankly, like build out an actual services business around it so that you can actually be there for developers. The analogy I like to use is like there's the core protocol, like Git, for example, but without GitHub, I don't think Git would ever be as successful as where we are today. Like, you need a website where I can sanely go look at the code, I can file issues, I can file pull requests, I can contribute, I can star, I can send it to the next guy. Like, without these things, like, it just becomes impossible to use. And I think that's where developers are kind of craving that at the moment, because this stuff just doesn't exist.
Yeah, I couldn't agree more. I think this vertically integrated full stack approach to, it's not just we have a core protocol and now have fun, go figure this out, but we have tooling that sits on top of Anoma that like you can sort of like get help along the way in order to actually deploy applications. I think the other thing that Ethereum incidentally did very well was Ethereum had just example applications on like ethereum.org, and I could download them and like deploy some Solidity. And it's like, we did this in like workshops in 2016 or something. It's like, here's a Solidity compiler, follow this step, now you have a dApp on Ethereum. And of course, dApps have become much more complicated over time, so the tooling has to become better. But I think this is really sort of hackathons, workshops, and then very good vertically integrated tooling. And actually on this last point that you mentioned where, with like off-chain data, I think current developers think about blockchains as computational platforms, where when you, for example, look at all the existing VMs out there, they're imperative. They're like 1 + 1 = 2, check that 2 = 2 in the, like this input, maybe change the color of the CryptoPunk, but this is really not what blockchain should be used for. Blockchains are for verification. Verification is generally cheap, and this is also where this is heading, I think, with zero-knowledge proofs, because they generally just tend to do verification on-chain, the verifiers live on-chain, but all this like off-chain data aggregation, how do you send intents around, who takes 100 intents and computes the right state transition that's verified on-chain. This is like, I think, a model that's going to be changing in the next couple of years as we get more adoption to zero-knowledge proofs.
Yeah, and I got sort of ZK pilled several years ago. I'm curious if either of you think there's ever, is there a fundamental trade-off where there's going to be a class of applications that never really should migrate, so to speak, to a zero-knowledge system? Or is this, because there's trade-offs everywhere, is there any class of application that you think shouldn't migrate or doesn't make sense for it to migrate to this type of framework?
So I think for now, I wouldn't migrate proof of stake to zero-knowledge based systems. Especially, like, you shouldn't I think you shouldn't put your fundamental security assumptions into zero-knowledge, because it makes it very hard for people to reason through whether they should be using this and they can use a blockchain securely, right? Like, if I don't know any of the validators or how the voting power is distributed or who's holding the voting power, it's very hard to build up trust in these systems. I think this is an application that will take years before we sort of should move this into zero knowledge.
Yeah, I think also speaking very candidly, there's a lot of concerns in terms of using zero-knowledge proofs as well, because when you can hide everything, you also don't know what was happening. Like, that's one of the beauties of like Web3 as it is today, is that you can go and look at everything. The downside is, of course, also that you can look at everything. But you know, the beauty is that like I can actually be confident that money wasn't minted out of thin air, because I can actually do a tally, and even more so that if the tally is wrong, I know how to fork off or roll back from that. When you're in a ZK universe, like think about like the concerns Zcash went through in launching, right? Like what if the ceremony was botched? What if there was some bug in the circuit? What if the proof system's broken? Like
There was a bug in the circuit.
and there was, exactly. And also the setup keys, there are a few elements that weren't supposed to be there that were there for a while, and it's not a good thing. But the point being is that like this gives you this kind of concern that if you have an environment, especially a regulated environment, where there's a high disclosure requirement or a high confidence requirement, like you really need to be sure that what you built software-wise is correct. Because on the theory side, I guarantee you, like you can come up with the perfect theories, it'll work, and you can get cryptographers to come and vet it. But as you know, like with every security scheme that's been ever built, there's always bugs in the engineering, and so that's where like one has to be extra precautious, and like, you know, it's almost like building like the ultimate space shuttle, where like every line of code needs like at least 100 lines of tests to correspond with it in order to build confidence that it was designed correctly.
I think actually one of the important things as we move more into a private state transition model is that there are sort of gates between them. There are firewalls between them. Like we have them in buildings for obvious reasons, that we have fire doors, and we should really think very carefully about at what interface level do we introduce these kind of firewalls. Like Zcash did this with when you had to upgrade from the old circuit to the new circuit, that they check the supply. And I think we should be doing this between a lot of systems. Like, for example, on the bridging side, when we move assets between bridges, we should have these firewalls that we aren't minting assets out of thin air. We should probably have this between dApps as well. The problem is it gets very difficult to build generalized firewalls. Like once you do arbitrary private compute, it's very hard to start building generalized firewalls. But I think at least for like assets, we should have a lot of firewalls there.
I want to dive a little bit more into proof of stake and zero knowledge systems. What do you think are the hardest challenges there, possible solutions? I know it's early, and the reasons why it's complex are sort of obvious in a way. The premise of proof of stake is that I can see everyone's stake. The premise of, you know, some of these privacy preserving systems is that I can't see anyone's balance.
I would add one shameless plug. Not a token holder, not investor, have no skin in the game on it, but Penumbra is doing like the shielded staking design. It's freaking cool. I think that one of the challenges, at least thinking about it from a traditional proof of stake model, is computational efficiency is certainly one of them. So when you're talking about like a few hundred validators, and you need to prove the state transition of all of these guys in one round in a 10-second block, and because you have to use percentage-based calculations, so you have decimals, floating points, and you need to make sure that the floating points are deterministic, you end up with a layer of complexity on top of a scale that traditionally, you know, when you do a zero-knowledge proof, it's usually for one guy doing one thing. And so like this kind of really blows up really quickly. So then what you naturally might want to do is to say, well, let me throw in some dedicated hardware like GPUs or whatnot. Well, the challenge then is that, you know, the domain of people who knows snarks is already like just tiny, right? But then the domain of people who know snarks and then knows GPUs on top of that and can verify that you wrote that correctly and you didn't introduce a bug in there is like even smaller. So
5 people most likely.
Yeah, and then to get that audited, there's no auditors for this. So
You are
like,
the auditor.
I think that the pain points are fundamentally that like the richness of the expression you're trying to do ends up being a huge bottleneck to safety then. But yeah, like I think that there are sane ways to do that, and frankly, like in Penumbra's case, their model is to say like everyone kind of just does it for themselves, and they update it based on conditions for notes that are on-chain, but you still settle things eventually effectively via basic normal computations instead of just the ZK bits there.
Also, if you want to find the Penumbra people, I think Henry and Daryl are
nice.
here.
Oh, I didn't know that.
A wave. You can talk more to them about private proof of stake.
It's cool tech.
I also think it's like historically we've been a little bit conflating the idea that like proof of stake should also make like, or staking assets should make very good money. And I think as soon as you start untying this, you can have like transparent proof of stake systems that support private financial applications, right? Like you can have a staking asset and you use DAI on top of it. So even though your proof of stake system is public, you're not sacrificing user privacy. And I think this is sort of like historically this wasn't true because generally we've tied the state machines to the assets. And so when we wanted to get something like Zcash, the entire thing had to be private. But now we can have like private applications on top of transparent proof of stake systems.
So, given that security in blockchains, is always based in a sense on the market cap, of the coin, right? Like the higher the market cap goes, in a way, the better the security guarantees you get of the computation in the system. How have you guys respectively thought about designing a system that has sort of economic soundness? What have been some of the trade-offs there, and how have you thought about making sure that for holders, investors, speculators, that it's a interesting asset for them?
Yeah, it's interesting. I mean, especially once you get into an interoperable world. But even on Ethereum, what happens if like the Tether market cap or like the token market cap starts eclipsing the value of ETH, right? I think from our side, we've been looking into one of the nice things is proof of stake systems. You can design them that they're relatively liquid on the native asset, which gives you, even though you may have more assets on the platform than secures the platform, it is very hard to acquire a liquid stake in order to attack the underlying platforms. On the other side, you should do like cubic slashing, where the more people commit a fault at the same time, the more they should get slashed. Again, as an incentive to one, remain decentralized, to make it hard to attack, and two, make it exponentially more expensive to attack these systems. And I think the third is like, once you're in an interoperable world, when you launch, you should probably have like gateways that limit, or like rate limits on how quickly assets can flow between these systems. For example, I mean, this was the wormhole Solana case to Ethereum, right? Where it's like $200 million moved in 2 blocks. And it's like, that is not a use case that normal people have. If you start slowing these systems down and how quickly assets can flow between all these interoperable systems, you probably end up in a scenario where you may get exploited, but you can also react to an exploit and ideally start mitigating it much more quickly than you can if everything can happen sort of in like a block or 2.
By the way, I think that, especially from Ao's talk about the concept of having like the ability to earn for contributing to privacy, like I think that that's a very cool incentive to bake into a protocol. I think in terms of like what we've been doing at Aleo, the design rationales have been complementary to these in the sense that, I'm a ZK nerd. I love ZKPs, and like the thing that I want to do is to be able to prove everything with it. And today you can't do that. So the protocol in and of itself is designed to incentivize what we call provers, basically zero-knowledge provers, to increase their proving capacity as much as possible. So in the consensus mechanism, we have this thing called the coin-based puzzle, which basically will mint new supply into the ecosystem for solving these hard puzzles. And every time a puzzle is solved, it gets harder, and it just continuously grows harder and harder. And the incentive for that is for teams, for example, I know the Scroll folks are here. Like for teams like Scroll or others who are building ZKVMs and have these crazy scaling capacities to do large GPUs or FPGA type designs. We want to incentivize them to say, look, if you have idle hardware that's sitting around, like use it on us in the meantime, because there is a revenue stream that you can generate by developing this while contributing to an ecosystem's supply, and then also growing market cap for all parties in the process by staking it. And the intent for that is to really try to scale up proving capacity, 1,000-fold from where we are today. Because like if you look at where cryptography on the web is today, like when you go to a website and HTTPS comes on, that padlock, like that computation, like 20 years ago would have taken several seconds. Today, it's like microseconds to do that. Why? Because back then you had to do it like on a Pentium 1 CPU in software or whatever. It was actually probably earlier than Pentium. But the point is that like it wasn't until people developed specialized hardware and then put this cryptographic chip on every CPU and shipped it standard in every device in the world did that technology become practical to be used like in the real world. And I think right now we're kind of at this inflection point where people are recognizing the value of ZK. They see that in software you can do this stuff and it can enable all these things, but there's no dedicated hardware. There's no like ZK chip on your phone yet in order to make these types of computations super fast. The existing cryptography ensures that data at rest is secure, but it does not ensure data in transit or in kind of in movement is secure, and that's what the ZK part lets you do. And I think that this is a huge value proposition in terms of just the incentives that we're trying to grow, and in that case for the utility of the token. Then
No ZK chip yet.
not yet.
So with that, thanks everybody. That's all we have for time for questions and everything.
We actually have time for 2 questions.
Oh, we have questions. Okay, great.
Anyone who would like to ask any questions to anyone present on the stage, please raise your hand really high.
We got one in the back.
Can somebody please send airdrop a mic to Henry in the back?
Yeah, so a question about the sort of, private staking. How do you understand if that's secure, et cetera? It's slightly motivated because of trying to build private staking. But I guess I have a question, which is, as a user of one of these systems, right? If I'm using some chain and then, oops, it turns out the economic security isn't there, and then all the tokens get stolen, that's bad for me. But also, if I am using this system and oops, there's a bug in the circuit, and now although I've got this transparent chain with some transparent economic security, if it's hosting a multi-asset shielded pool that turns out not to be sound, I'm still losing all my tokens, right? And so I guess I'm wondering, to what extent does cutting the sort of network stakeholders out of participation in privacy actually change the risk?
Yeah, I think maybe, well, it does change the risk, because I think for an ordinary user, it is much easier to look at sort of what are the current validators and how much stake do they have, to be able to at least get an intuition on what is my underlying security risk, right? This is true that if there are bugs in the circuit, you still have this problem, but there you can also do defense in depth, where you start having sort of rate limited withdrawals, and you have the withdrawal gates. So I think, to me, this is mostly a question for now about defense in depth, and it's easier if I only have to reason about the security of my circuit than if I have to reason about the security not only of my circuit but also my private governance system. I, for example, also wouldn't necessarily build a private governance system at the moment for kind of the same reason, I think. But I'm very excited about the experiments. So,
I'd be curious if there's also ways to kind of enforce people with the turnstile mechanism that Zcash uses, but maybe on a per epoch basis to try to force state to kind of reconcile. But yeah, I'll be frank in saying I haven't thought very deeply about this particular domain, in part because it's not an area that I've looked at a lot, but nonetheless that I think that there are ways to mitigate risk if you're willing or able to, in a system, disclose some type of either the direct information or just kind of some metadata associated with it, so that you can prove the tallies of either votes or state. Yeah, I guess in theory you could also roll back a few blocks and fork, but I don't know if you want to do that. So.
Right, any other questions? Mic to Mic to James.
Hello. Oh, hi. Thanks, Alex, for the talk. Howard, to your point about wanting to zkp everything, and also your comment about the hardware limitations for HTTPS, do you think there's is hardware, as it stands today, or where it might go, a rate-limiting step to the expansion, the proliferation of ZKPs in sort of more mainstream use cases beyond sort of, very esoteric scaling stuff, but maybe more consumer use cases in terms of whether it's laptops, desktops, mobile, anything like that?
I think that it's it's dependent on the scale of what you want to do. So if you're talking about like Zcash payments, like I think the answer is probably no, like you're fine. But I think that for a lot of the applications that, at least that I see, especially in terms of just the web and what you want to do on the web, I also just think about a lot about fairness, and in machine learning models, you want to prove fairness about executing. There's a lot of, in terms of criminal justice, there's a lot of motivations for these types of systems to demonstrate fairness, that for those types of computations, those today are slow on ZK systems, but ZK systems are incredibly well motivated for proving those exact types of statements that a court could actually admit. For things like that, and that's why I'm saying, like, I'm looking kind of 10 years out in terms of the types of use cases where I see this being just commonplace in our day-to-day lives, that technology is going to require specialized hardware. And if I want like traffic camera systems, or I want biometric data to be provably only stored and used here for these purposes and not anywhere else, like, you need ZK at a scale that just does not exist today.
And I wouldn't say we're going to get to like where everyone buys like a new card for their computer that's like the ZK card, like your kind of graphics card. It's most likely going to look more like the CPUs, where like specialized instructions in the instruction set on a CPU will just be there to support ZK operations. So like over time, Intel will like implement new opcodes effectively, or instructions in the CPU to support ZK operation.
I look forward to this ZK SGX.
It's going to be cool.
Thanks, guys.
All right. Thank you so much, Olaf, Howard, and Adrian. Let's bring your hands together for this amazing fireside chat. I think these guys are going to hang around, so if you had more questions, go and catch them. Okay, we're going to be going to break now. See you at 10 to 7. Hey everyone, we're starting again. Please take a seat. Please take a seat. Felipe, can you go around and see who wants to take
Okay.
back down?
Yeah, sure.
You're speaking now.
So, yeah,
Somebody needs to. Just give it a couple of minutes until people sit down.
just tell me when to start. All right. So I'm probably gonna stand and do some I got these slides. Actually, I'm this is the same slides I gave in the other thing. I updated it a little bit, and then this. Okay. So then I'm just gonna start chatting, just kind of free format. And they asked, I'll ask if I can kind of cut it down to 15 minutes.
Everyone, please take a seat. We're starting again with program. Especially all developers out there that are gonna get into building godlike technology, you are gonna be really interested into this joint tech. Cool. So next up, we have Alex Pruden from Aleo presenting the Z Prize.
Hey, everybody. Thanks very much for being here. Very thankful that it's not as hot as it was yesterday. Otherwise, I can only imagine what it would feel like down here. But yeah, I'm excited to talk to you guys today about. So I'm Alex. I'm the COO of a project called Aleo. But I'm not here to talk about that yet. I'm speaking about that a little bit later. But I'm here to talk about something called the Z Prize, which is not an Aleo initiative. It's not an Anoma initiative. It's not any one company's initiative. It's something that we're doing together to accelerate the future of zero-knowledge cryptography. So I'm really excited to share more about that effort over the next few minutes with you. So, okay, so what the motivation behind doing this collaboration. So I guess maybe quickly, what is the Z Prize? So it's a collaboration between 32 companies across the zero-knowledge space, sort of modeled after the X Prize, for those of you who are familiar with that. So it's kind of like generational problems, and you put some money behind some prizes that you think might kind of move the needle in one direction or another, or at least, well, in the direction of development to hopefully make these technologies more practical sooner. So, yeah, and one of the problems that inspired this effort was that teams like Anoma, Aleo, Aztec, Mina, and it's just a handful of the teams that are sponsoring, are in-house doing a ton of development of like things that are pretty low level and transferable across, across teams, across proof systems. And the thought was to try and inspire people to work together on these problems that were relevant to basically anyone who is using or is using zero-knowledge cryptography. And so that's basically how the Z Prize came about. Yeah, so like I said, it's an industry-wide competition. The X Prize was the inspiration. And the key thing for this is, you know, the requirement, I guess the model of the Z Prizes is a competition where, you know, sponsors, one of which is Anoma, and I'm going to bring up Adrian in a minute. But the format is sponsors put up money, and then applicants apply to try and solve these problems to earn the pot. And all of that work gets open sourced to hopefully create a foundational library for some of these lower level primitives that make up zero knowledge proofs, and hopefully therefore inspire the next generation of protocol innovation. Yeah, cool. So here's the goals of the Z Prize. So most of you, I think, in the room are probably developers, so you probably know that zero knowledge proofs, under the hood, there's a lot of different algorithms that are going on. And so the idea of Z Prize is basically like peel back a layer from like, okay, Plonk and Marlin and all of these like high-level proof systems and look at, for the most part, lower-level primitives like multiscalar multiplication, fast Fourier transforms, those types of things, and trying to accelerate those lower-level building blocks so that, you know, you can build up to a faster than implementation of Plonk or Marlin or whatever it may be. Cool. So the way it's broken down, and by the way, this effort started officially in May, and proud to say that so far we have 70 different competitors from across the world competing for, like I said, $7 million worth of total prizes that was sponsored by 32 companies. And it's broken down into two kind of sections. We have the open division, which the idea there is like really focusing on problems that apply across the board. So an example of an open division prize is, like I said, multiscalar multiplication, which for pairing-based ZK snarks account for, you know, the majority of the computation. So most of the work that you're doing is you're computing these MSMs, and so that there's a prize specifically about increasing, you know, throughput of producing multiscalar or computing multiscalar multiplications, which again is relevant to really anyone using pairing-based snarks. And so that's the idea of the open division, is that you kind of get collaboration across teams, and multiple teams come together to sponsor it. In fact, the one I just referenced, I think there's 5 sponsors from across, you know, 5 different sponsors for that prize. And yes, that's sort of supposed to be more of a collaborative one. And then the team division is one where, you know, say Aleo has a specific, hey, we have this one specific algorithm that we want to accelerate. That's sort of what the team division is for. So, you know, kind of keep room for both a, you know, a collaborative effort as well as like individual team bounties effectively. So here's the Open Division Prizes. Like I said, this kicked off in May, and we've got a lot of progress on this so far. So the MSM NTT acceleration. So this is, again, these are like kind of the lower level primitives for zero knowledge proofs. Accelerating those, and that's sponsored by Aleo. We've got a prize that's focused on doing the same thing except in WASM. So as opposed to like the first prize, which is really focused on accelerating those on a server type environment or runtime. This one, the second prize, is about doing the same thing but in a WASM type runtime, which is what runs in your browser. So more applicable to a client device that maybe is computing a proof. Like if you're running a browser and you want to compute a proof in your browser, that would be applicable there. Some relevant to PlonkUp, which is Plonk is a protocol that many teams are using now, and there's some other things that again are kind of relevant across the board. For the team division, again, like I said, this is some more specific stuff, specifically for Aleo. And I guess the one I want to highlight here, because I think it's actually relevant for more than just Aleo, is accelerating verification. So a lot of times the focus on optimization is on the prover, because typically in most of these protocols, the prover is kind of heavier weight as a part of the system, but there are cases where verification becomes a bottleneck, and you're starting to see this in some ways in the rollup context where verification is very costly, and so if you can have a more efficient or faster verifier, you could potentially pack more into a rollup transaction in a block. So so anyway, that's one that we're pretty happy to sponsor. This is something that's directly relevant to Aleo, because for us, effectively every transaction on Aleo is kind of like a rollup transaction. But again, like this year, these team division prizes are kind of specifically about the individual projects and what they're doing. I'm about to bring up Adrian so he can talk about the Anoma one, so I'm not gonna ruin the surprise there. But this is running for the next 3 months and ideally beyond, because again, the hope for this is to have an organization to basically come together under the roof of which people can come together and collaborate to build this technology. I think fundamentally what unites all of us, I mean, we all use different proof systems and primitives, and we have different, branding and everything like that. And all the projects in the ZK space differ in important ways, and that's great. But I think what unites all of us is a belief that this technology is going to fundamentally be transformational. And I think no matter how much we each do independently, I think we'll only move as an industry as far as we can collaborate together. And that's the idea of this, is to be a basically neutral ground where we can come up with these innovations together, kind of put some incentive behind it, and then hopefully build this infrastructure that can help all of us, like I said, make this technology practical sooner. Yeah, cool. I said all this. Adrian, why don't you come on up and, we're going to kind of a little bit impromptu. We decided to not do slides.
All right.
But I'm gonna do a little fireside chat. You want to sit down? I kind of want to sit down.
Good to be back.
Welcome back. Long time. Hopefully you had a drink. So anyway, Anoma, we're very proud to feature as one of the gold sponsors of the Z Prize, and Adrian and his team in general have been extremely supportive of this effort and done a lot of work to make it happen. And so I want to give Adrian a chance to kind of give his perspective on this. So maybe first, my first question is, what do you think in general? What was your reaction to this when you saw it was announced? And I guess, what do you think of the Z Prize?
Yeah, I mean, I'm very happy, and big thanks to Aleo here for actually pushing Z Prize forward. I mean, you guys were the driving force behind getting this entire competition together and getting it off the ground. I think it makes a lot of sense. I mean, we have some very general prizes in the open division to just focus on making plonk up faster effectively, and then some very specific ones to Namada, which is we want to get very fast browser-based verifiers for Groth 16 for our specific second Groth 16. So I think it's a good idea. I think we are currently still behind in terms of how good the hardware and as well as the software is for both the verification as well as the proving. And especially as soon as the provers get way faster, we can do a lot more generalized compute that people can submit generalized proofs that they generate in browser, for example.
Yeah. So you mentioned something there that I actually neglected to mention, but it's important, is that one of the dimensions here where competitors are really innovating is around implementing some of these algorithms in hardware where it maybe hasn't been implemented before, right? So either optimizing a GPU to do lots of MSMs or having an FPGA compute NTT or FFTs. And so I guess there's a lot of hardware startups focusing on the ZK space now. I'm going to ask you a little bit of a tough question. What do you think? Is GPU acceleration or FPGA acceleration going to be the future for ZK snarks in terms of hardware? What's your gut tell you?
I think it depends.
Classic answer.
Right. I think short term, GPUs are going to. I don't know. If we get to the point where we spoke about this with Olaf and Howard here, where once Intel starts shipping specific instruction sets that that effectively are almost like an FPGA, but in an Intel CPU, at least I can kind of think about it this way. I think at that point, specialized hardware will win. In the short term, everyone, no one is going to start buying these FPGAs. It's going to be on GPUs.
Do you think in the next 5 years we'll see the development of a ZK ASIC? I guess what you're kind of saying, if Intel kind of integrates some of these instructions, then that maybe is a weaker form, but an ASIC in the sense of a Bitcoin miner ASIC for ZK proofs.
Yeah, I don't know. I actually hope not even, because I think it'd be, you have this problem with even Bitcoin miners that once you need specialized hardware, people have a massive game theoretical edge over the general population. So actually I hope it remains in commoditized hardware. And we just have very fast implementations on off-the-shelf hardware.
So maybe this is a good transition for you to talk a little bit more about the prizes that you guys are sponsoring, because you mentioned one of them is specifically about browser-based verification, right? And maybe, just if you can tell us in a little bit more detail about what those are and why they matter to Anoma.
Yeah, so the Team Division prize is very simply if you can optimize the mask circuit for Groth 16 as much as possible to run in WASM. That's wonderful because the faster that is we can put it on even lower performance edge devices effectively. sorry, not the verifier, the prover. So where like a shitty phone should be able to generate a proof for the MASP as quickly as possible. Because that allows people to build wallets that work with Namada that can run on low quality hardware. So that's sort of very simple. It's an established proof system. It's a relatively straightforward circuit. And so the ask is very specific. And then more generally on the Open Division, we are using PlonkUp for pretty much all of our circuits. So if you can optimize the hell out of this, it's also wonderful. It makes generalized compute it makes a lot of things, a lot of kind of circuits you can write that use PlonkUp a lot faster.
Nice. Well, I think we're actually out of time. We got to move the schedule along. But someone should ask Adrian during the break what he thinks of the different flavors of Plonk, or Luke Pearson if he's around, because Plonk is a very prolific ecosystem. There's a lot of different flavors out there, and I think everyone has opinions about which of them will be, I think, the future. So
Indeed.
Good question for the break. Go find this guy. It's pretty easy to find, as you can see. That is it for my slides. I guess the last thing to highlight is I mentioned there's a lot of teams supporting this. Here's a few. Of particular note, I'm proud to say that we got AMD and Samsung, so some two manufacturers of hardware that are supporting this, which hopefully goes to show all of you that people outside of just the Web3 conference circuit actually are interested in zero knowledge and believe in its potential. So yeah, really happy to have collaboration with them. Thank you very much for listening to my talk.
Julia. Next up is Julia from the Anoma team. And Julia will be giving an introduction to Taiga, one of the projects that our team has been working on.
Hi everyone, my name is Julia. I work at Anoma as cryptography researcher, and I'm gonna talk about Taiga. It's gonna be an introductory talk, so no deep crypto. Everyone should be able to understand it, I hope. This is the team behind Taiga, so you could appreciate their work. Joe, Alberto, me, Iraklis, Simon, and Shriyang, ordered in alphabetical order. So, yeah. So, about Taiga. What is Taiga? Taiga is a protocol for private multi-party bartering on Anoma. Well, that's cool, but what is multi-party bartering on Anoma or everywhere? Well, imagine we have a bunch of users that has something and they want to get something in exchange for that. For example, we have Yoshi, who has an egg and wants a star. We have a Bowser, who has a star and wants a mushroom. And we have a Mario, who has a mushroom and wants an egg. We can see that none of them can satisfy the needs of one of the others. But if they combine in like a bartering cycle of 3, they can perfectly satisfy each other. And that kind of transactions is possible on Anoma. It's kind of cool because it's implemented as a single atomic transaction, and compared to the usual approach of multiple transactions, it's better because parties who do the bartering won't end up in some kind of intermediate state. Like, for example, if Mario decides not to have an exchange with Bowser, Bowser ends up in intermediate state owning the egg that he didn't really want, instead of being in the same state as before. And with atomic transactions, it either happens fully or not at all. And it's also cool because when you have just one transaction, you pay fewer fees, which is nice, and it might be convenient for dealing with rare items. Every valid transaction on Anoma is authorized by validity predicates of all of the involved parties. What is a validity predicate? A validity predicate is a user-defined piece of code that authorizes a transaction. And if a transaction changes the state of a party, its validity predicate is called to authorize the transaction. Like, for example, if it's a transfer and receiver sends some money to someone, then both validity predicates of receiver and a sender will be called because it changes the state of both of them. So back to Taiga. What is Taiga? Taiga is a protocol for private multi-party bartering on Anoma. And by private, we mean that identities of the users, amounts of tokens they spent, and the types of tokens and validity predicates of these users will be private, which means that an observer who sees a transaction on a blockchain don't know what's going on in this transaction really. Now, how it's done? We use zero-knowledge proofs to facilitate private transactions in a similar way to Zcash, Zexi, and other similar projects. To create a node, you commit to it and publish in a public tree, public commitment tree, and then to spend this node, you prove in zero-knowledge that this action is allowed, that this node exists in the tree, that it hasn't been spent yet, and that you're actually the owner of this node and you can spend it, and some other checks. Now, as I mentioned, we use validity predicate to authorize transactions, and we also make them private, so an observer only knows if it's valid, if it's evaluates to true or not, but not the conditions on which it evaluates to true. So as a result, we get that identities, amounts, assets, and validity predicates are all private, and we achieve data and function privacy. Well, compared to transparent Taiga, transparent multi-party bartering on Anoma, it would look like that. You can see that some kind of exchange happened, but you don't know who are the parties involved, you don't know the content of validity predicates of these parties, and you don't know the tokens they're exchanging. And in fact, it would be more something like that. You can see that some parties exchanged or did something on the blockchain, and they exchanged, like sent assets to each other, and that all of the validity predicates involved are satisfied. But you can't really tell if it was just a transfer or exchange or bartering, multi-party bartering, or whatever. So, in fact, Taiga is a framework for generalized private multi-party bartering, which means that it's a framework for private state transitions, because generalized private multi-party is just any kind of state transitions. Some of the features of Taiga. At first, we were focused on bartering applications, so we make sure that we have a good ecosystem for implementing these bartering use cases, but other types of state transitions are possible too. Writing validity predicate circuits that describe the preferences of the parties involved are made easy. So we provide a high-level language that is practical for writing validity predicate circuits, which is called JUVIX, and we also provide intermediate representation for circuits called Vampire, and you'll probably hear more about it in one of the next talks. And we're also going to provide a library of various examples of validity predicate circuits for users who don't want to write their own validity predicates, but still want to use Anoma for privacy or for whatever reason. But if you want to write your own custom fancy validity predicate, you can do it too, of course. Some of the examples of these validity predicates could be whitelist, where you choose from who to receive assets, or signature check, which is basically what Zcash does, or some other types of circuits. And it's also possible to integrate with transparent Anoma because the architecture is basically the same. We have validity predicates, we're intent-centric, and all of the features of transparent Anoma are supported in Taiga. Now let's compare Taiga to the existing products that are privacy preserving, so we could see the difference. First of these products is MSP. For those who don't know what the MSP is, it's one of the products of Anoma called multi-asset shielded pool that, as the name states, allows for assets to share the same shielded pool. It's based on the sampling circuit, but it allows to store arbitrary assets, so all of the assets benefit from the shared anonymity set. And MSP is available on the current Namada blockchain implementation, and Namada is the first fractal instance of Anoma. So you can ask, if I have MSP for privacy, if I can just store all of my assets in MSP, why would I use Taiga? Well, MSP is a very nice option. It guarantees you private transfers of multiple assets, which you can store in the same shielded pool, so it's cool. But Taiga is a more general and suitable for different kinds of applications that might be not possible with MSP, like multi-party bartering, or in general, any kind of application you can ensure with validity predicates. Well, let's now compare Taiga to very Zexy and Zexy. What is Zexy and what is very Zexy? Well, Zexy is a ledger-based system that allows users to execute arbitrary computations offline and prove the correctness of these computations, which means that users can have predicates for the records or the nodes that they create. And to create a node, the birth predicate has to be satisfied, and to destroy the node, the death predicate has to be satisfied. So very similar to Taiga, actually. Very Zexy is just a version of Zexy with accumulation and universal setup. So just for illustration, you can see that a transaction on a very Zexy or Zexy blockchain would look like something like this. We have parties with hidden identities, they exchange some kinds of assets, and we just know that all of the predicates are satisfied. So you can see it's pretty similar to Taiga. So comparing these two projects, we can see that, yeah, the architecture is basically the same or very, very similar. Both projects just use private programmable predicates to validate transactions. In case of Taiga, it's validity predicates, and in case of Zexy and very Zexy, it's birth and death predicates. And both projects, well, comparing to very Zexy, both projects use Plonk as proven system. Which is nice because we can use all of the advantages of Plonk research and use all of the optimizations. There are some differences. As I mentioned before, Taiga is mostly focused on bartering, and we have a strong validity predicate ecosystem and tools for writing them. And Zexy and very Zexy kind of are generalized, so they don't have preferences in the use case, let's say. They don't really provide options. No, they provide options, but not specific predicates prepared for people to use. And some of the implementation details are also different, but they are minor, I think. The current state of Taiga, well, the project is still in early stages, so this talk is more like to introduce you to Taiga, to let you know that it exists, it will be working soon, and many details remain to be confirmed, like low-level details. But the proof of concept code is already available at github.com/anoma/taiga. and you can follow the work we are doing. Well, actually, that was the Taiga 1. It was the first version of Taiga we are working on. But there are going to be Taiga 2, which is going to be even cooler. So what is the future of Taiga? For Taiga 2, we're planning to have programmable data transport across public, shielded, and private domains, which already been mentioned. So by public, we mean transparent, like transparent Anoma or transparent domain. By shielded, we mean zero-knowledge proofs, which is a single user private state. And by private, we imply FHE, which is multi-user private state. And we also going to have closer integration with Feria. Feria is one of our products which helps against, well, for front-running protection. And in Feria, you will be able to prove correspondence between private state and data encrypted to Feria using zero-knowledge proofs. I think it's very cool. So I guess that's it about Taiga, and you can send me an email if you're interested in it. Again, another link to the code if you want to follow the project, and I guess it's time for questions, if you have any.
Unfortunately, we are a little bit behind schedule, so we won't be able to take questions. But Yulia, you will be around, right?
Yeah,
so
yeah,
please
yeah.
grab her questions. Thank you so much.
Okay, thank you.
Next up, we have Howard again on stage, and Howard has really exciting updates about Aleo.
That's all right. All right, how's it going? This talk is called The Last Mile for ZK because, as you guys know, the last mile problem is always about the hardest part of getting things to consumers or to customers or to users, to developers. So the point of this talk is, one, to give a quick update on one, what have we been doing, and two, what are we working on, and three, where are we going? So let's jump into it. To start, for those who are new to Aleo, I want to just give a quick overview on what Aleo is. Fundamentally, it's a platform that lets you write zero-knowledge applications. That's the idea. In order to make this happen, there's really three main parties in the ecosystem that we ourselves are trying to support and also build a community around, and that's developers, that's provers, and that's validators. The idea here is that developers, they run applications, they create applications, and they send requests. These requests go to provers. Provers execute these things. A user themselves or a developer themselves could be a prover as well. So it's worth pointing out that these parties may not be mutually exclusive. But the point is that provers execute applications, and they execute them at scale. These things get executed into transactions that are broadcast onto a network where validators basically admit them via consensus and then sends the results back to the developers or the users. In terms of what we've been working on to make this thing happen, well, one of the things that we've been developing thus far has been, in terms of networking, there is a lot of communication overhead that goes into actually getting this type of richness of application state across all users. And so we have been building out, there's a paper called CADCAS, which is a protocol that is similar to Kademlia, whereby it allows you to, via a topology, discover other nodes and quickly, effectively propagate information to them with a high guarantee that it's widely distributed and widely disseminated amongst that network. This is something that we think is going to be absolutely necessary or critical in order to get data out there at scale with speed. Going into the ZK side of things, I think one of the things that's also worth bringing up is, so the proof system that we use is called Marlin. Marlin itself is a universal and updatable zero-knowledge proof system. It is similar to Groth in the sense that it uses R1CS as the expression or the underlying representation to write actual programs in. But with Marlin, we have done some some fun work with it. Namely, one thing which you guys who are familiar with the Plonk community familiar with is lookups. The idea that I can basically create these kind of custom constraints and look up specific values in order to use them in specific operations. So for example, if I want to create like a hash function, or if I want to create thereby a Merkle tree that's far more efficient than what we're traditionally used to, that I can create like this table, look up values from it, index it in, and then use them direct. This is something that we've been able to effectively build into the current Marlin schema, and it's something that we're very excited about using. We think that it's going to give us a very, very performant prover with that. The other aspect with respect to Marlin that's worth bringing up is this design actually allows us to do batch proving. So what do I mean by that? Well, normally when you want to execute a transaction, let's say it's a transfer, and you want to send to 5 different people. You might do 5 different transfers, right? So the cost is linear. You basically pay 5 times the execution time, right? With batch proving, the beauty of it is that you can actually effectively bring things down to close to just 1x. So if I want to send to 5 people, it's just slightly more than sending it to just one person. Ditto if you want to send to 10 or 20 or 30. It's a way to aggregate the actual computation and batch these executions together. And it's something that we're very excited about in terms of scaling up designs. Naturally, you can almost think about like, there's rollups out there, people love rollups, and this naturally gets you very efficient, very fast rollups. And so it's something that we're looking forward to using as part of the underlying compiler system that we have coming out in testnet 3, which I will get to in a moment. Another thing that's worth bringing up is threshold signing. This is another cryptographic primitive that we've been working on, and as an update, we have been able to get out some new work in terms of Frost. We've tailored the design for our specific addressing scheme, and for the cryptographers in the room, the gist is that we needed to update the verifier challenge to include some additional group elements that pin it to the exact commit, or basically commit to the exact schema that we have with our private keys. But the high-level idea in terms of threshold signing, for those who are unfamiliar, is that say I want to move a transaction from A to B. Normally, what you do, you just sign it yourself, and then you move it on. But sometimes maybe that key is very sensitive, and you don't want it yourself. So what you do, you can share this out to a number of people, and this gives you a way to effectively allow a large group of people, some who you may trust, some who you may not trust, to basically create a transaction for you. And none of the parties in this particular model would learn the private key in doing this process. And it allows you to do a threshold of them, so that this way, if some of them go offline by accident or intentionally, the protocol remains resilient. It's one of the things that I think has been, well, frankly, missing in a lot of L1s, but it's something that I think we're very excited about getting out there. All right, and then the last thing before I jump into the main plans is Coinbase puzzles. So for those who have been familiar with testnet 2 on our front, we had this thing called proof of succinct work, POSW. And the idea with POSW is to say provers can basically solve this puzzle that allows you to generate a proof that is used for, well, one, minting new supply into the ecosystem, but then 2, also for getting a incentive to actually develop faster and larger hardware. And I'm really excited to announce that we have a new design with the Coinbase puzzle, one that I think a ton of provers are going to love, which is that we've focused it down to its core, which is MSMs and FFTs. For those who are unfamiliar, MSMs are multiscalar multiplications. They're like multi-exponentiations, if you're familiar, where you have different group elements in the base, and then you have different scalar elements in the exponent, and you're basically trying to efficiently compute like g to the x1, or g1 x1, g2 to the x2, g3 to the x3, dot, 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 and so on, and compute one value out of it. With FFTs, that's fast Fourier transforms. It's a signal processing algorithm that, in this case, allows us to do polynomial multiplication very efficiently. And with this new design, what we actually end up with are proofs that can be roughly 100 bytes in size and about a millisecond to check. And for a schema like this on chain to mint new supply, we think that this is going to be a huge win in terms of getting a fair distribution of tokens out there to provers who are in the ecosystem. A much more formal and well-documented write-up will be coming when this comes out. I know I'm running short on time, so let's jump right into the main thing, which is we're really excited to announce that testnet 3 is going to be coming out. Testnet 3 will be coming out in 3 phases. The first phase comes out August 1. And we will be bootstrapping a network with what we call Genesis beacons. These are going to be the nodes that basically set the Cannon chain in place. Anyone will be allowed to install SnarkOS in this case, run a node, and basically sync with the network. Developers from day one will be able to write programs, deploy them, and execute them on the network. And that's something that we're very excited about getting out there literally in, I think, 2 weeks. Yeah, 2 weeks. Yikes. But on to phase 2, September 1. Yay, more time. With phase 2, we are going to be releasing these coin-based puzzles. So provers will be able to start producing proofs that are going to be checkpointed into blocks. Provers will be able to earn credits as part of doing that. And separately, we'll be kickstarting a bug bounty program for Snark OS and Snark VM. This will be open to the public. Anyone can participate. And we're very excited to try to find all the bugs. Like I keep catching bugs, so I look forward to people's submissions. I hope none for funds, but yes. Lastly, for the third phase, which I think is going to be the most exciting, is October 1, we will be opening up the network to anybody to validate. Any prover who has accumulated 1 million Aleo credits to start will be able to become a validator. Any other person, anyone else who has tokens, can delegate them to existing validators by bonding and also removing stake by unbonding on the network. The incentives in this design will be fully laid out in writing, but to give you the intuition for what we're doing here, the goal with Aleo's consensus mechanism is really to incentivize hardware acceleration for zero-knowledge proofs. That just does not exist in the ecosystem today. We think it's a vital part of bootstrapping ZKPs for this next decade. And for the people who make hardware today, one of the big challenges is that they just don't have the ability to actually incentivize themselves even to manufacture custom chips for it, because there's just not enough revenue streams for it. We want to use this as a bootstrapping mechanism that allows them to actually back themselves into dedicated hardware and go and basically incentivize them to go and execute proofs with this. Naturally, the puzzle we've designed here is also going to tailor for hardware that will speed up actual programs on the network. And so as a prover, you kind of have a free option of saying, if there are jobs to execute, I will execute normal execution requests from users. If there's no jobs in the moment and my machines are sitting idle, I can go and work on these puzzles in order to mint new supply into the ecosystem. And that's the high-level idea here. We think that with this design, first off, the reason why we need validators in this design is someone needs to keep the provers in check, because they won't be able to keep themselves in check. So with validators, the rationale is that honest validators who are staked will be the judges in this. They will enforce that the provers actually hit the targets that were required via consensus to be admitted, and that the correct amounts were issued to them via these issuance mechanisms. But yes, this is coming October 1. We're very excited about that, and I think that will be a huge part of what's to come. I think there's supposed to be one more slide, but maybe it got lost. Well, I guess the last slide was to say thank you, but also that we are doing a developer workshop tomorrow. The developer workshop, if you go to lu.ma, Luma, lu.ma/AleoEthCC, you can sign up on there. I think we're actually at waitlist, I think. But nonetheless, if you sign up, we can get you guys a response later today. Oh, and there are cards at the table there with a QR code? Okay, with information about it. And so if you guys are interested, feel free to hop over there and grab a link. Look forward to seeing you there. And that's my talk. Thank you very much.
All right, next up is Paul and Joshua from the Anoma team. And they will be representing Vampire and Jivix.
It's good. Okay, everyone, thanks for waiting. So I'm really excited to talk to you about a project at Anoma called Juvix. So Juvix is lovingly created by all these people here, Jan, myself, Lukasz, and Jonathan, and with the help of Tara, our mascot, the most important person in the team. So what is Juvix? Well, it's an open source programming language, and we want to support writing Anoma applications. So we heard earlier about high-level languages for writing ZKP circuits. So Anoma is intended to target WASM for the public execution and ZKP circuits for shielded execution. So, question, why have another language? Why Juvix? Well, we want to have we want to have a unified platform for making these Anoma applications, and it's really important that we have really great tooling, really great compiler that can help users write the programs. And we also think it's important that we have a very expressive type system in our programming language, because the more we can express in our types, the more the compiler knows about what we're trying to do, the more the compiler can help us write our program. So we think this is a really important thing that we can build into Juvix. And we want Juvix to compile to efficient WASM programs. We want them to be small. We want them to be optimized for running on Anoma. So where are we today? Well, we have two projects, one called Juvix and one called Juvix Circuits. So Juvix itself compiles to WASM, and Juvix Circuits compiles via Vampire, compiles ZKP circuits to Vampire, which is Joshua will talk about in a minute. And eventually we'll have Juvix as a unified front-end language, high-level language to support both writing validity predicates for Anoma and ZKP circuits. So that's where we want to get to. Well, what I really want to do is show you how Anoma looks, how Juvix looks with some examples. So I'm going to attempt to do this here. Okay. Let me try and change this to mirror. This is going to be impossible. What's that? Yeah, I'm trying to go to the display settings, but I cannot see. Well, my mouse is on this screen. Oh, right. This. No. Where are we? I think. Maybe I'll just go back to the slides. Maybe just go back to the slides. I've got some backup slides, just in case. Okay, sorry I can't show you a live demo, but I have some example code here. If I could just... Okay, so first thing you want to see is Hello World program. So this is what Hello World looks like in Juvix. So the syntax is similar to something like Agda or Haskell. So you can see the pure functional programming roots of this. Here is a more complicated example, Fibonacci. So we can see here that, like in Rust, you have like a match construction. So we can match on the zero and successor functions of the natural numbers to define Fibonacci. And we can define user-defined inductive types, and with some polymorphism, so we can reuse code in different contexts. But unfortunately, I can't show you the actual demos that I wanted to show, but I'll hand over to Joshua now, who's talk about Vampire.
Hello. All right. I'm going to talk to you guys for a little bit about Vampire. I apologize. I made like 80 slides, and I have time for like 7 slides or something like that. So I might go through some of these very quickly or skip some. Vampire is a language for arithmetic circuits. And so a good question is, why do we need a language for arithmetic circuits? An example I can tell you is Anoma has the MASP, which you've heard about several times. And it is written as an arithmetic circuit in R1CS and uses the Bellman library. But we wanted to explore implementing the MASP in other proof systems like Planck, maybe Halo 2, for instance. So I set out to try and rewrite the MASP in these other libraries. I tried to rewrite the MASP in Planck first, and it was a big pain. Like Howard, I have spent a lot of time handwriting circuits. I get a perverse pleasure from handwriting circuits, but it's not what you really want to be using your time on. Might be fun to waste an afternoon trying to prove that these two systems of polynomials have the same solution set and so on, but it's not an efficient use of time. And that's kind of what you have to do. These different proving systems, they have a different structure for circuits, so you have to kind of look at the polynomials and do a lot of like grade school math, trying to figure out what are the right polynomials that you need for your system, when really you are describing the exact same thing at its core. So what we want to do with Vampire is have a way of specifying an arithmetic circuit that is universal, so it's portable to any other proving system that uses arithmetic circuits. Vampire is our language for doing this, and it can also serve as a target for DSL. Vampire by itself is, you could call it a DSL, but it's missing some familiar programming things like loops and conditionals and so on. It's a language for expressing circuits, not really a language meant for programming. If you want to do that, you can use a front-end language that compiles to Vampire and then compile from Vampire out to whatever constraint system and proof system you'd want to use. Paul talked a little bit about Juvix. We want Juvix to compile to Vampire. We also have another DSL compiling to Vampire called Alucard. It's a Lisp-based DSL. I put question marks here because not confirmed yet or anything like that, but there's some interest from the Socrates folks about Vampire as well. I want to show you how arithmetic circuits are represented. Here's two arithmetic circuits. An arithmetic circuit is a representation of the computation of a polynomial. So here are two arithmetic circuits. They really are kind of like circuits. The name, it's a good name. So I kind of drew these as like printed circuits. These two circuits encode the same polynomial, but the computation is done differently, so the circuits are a little different. You can join two arithmetic circuits together just by wiring them up. So if you imagine that some kind of voltage is applied to X, Y, Q, R, et cetera, if you wire R to Z, then if you apply a voltage to R, you have the same voltage as Z. I'm not an electrician, I don't know if that's actually true, but in circuits it is. And in fact, this wiring here would be what you would need to do if you were doing a modulo operation by something that is, if you're doing mod 16. You have a range proof over here, which shows that the input to it, the primary input Z, which is connected to R, so it's the same as R. The remainder is less than 16. Arithmetic circuits also specify a system of polynomial equations. So here's that range proof. This is a 4-bit range proof from before. You could also think of it as a system of polynomials like this. Uh-oh. You can also think of arithmetic circuits as a list of gates and wires. Here I have a kind of flattened version of a circuit. It takes 5 inputs. You can see it's Z, A, B, C, and D. And then in a particular order, you apply operations to those inputs. You multiply A times A, B times B, C times C, and so on. So this is another representation of that range proof. And over here we have equations, equalities. This is like wiring. 11 and 0 are equal. That means we're drawing a wire from 11 to 0, and those must take on the same value. Okay. I am going to go through this quickly because I'm starting to run out of time. But I'll show you, this is what Vampire looks like if you want to write in Vampire. Basically, you can define an alias. An alias is a name given to like a sub-circuit. And critically, you can also give it a signature, like a function. The signature tells the compiler how to compose circuits. Circuits don't have like a natural composition, but if you include the signature, you can compose them, and it works fine. All right, so here's some examples. We have a circuit that checks that x is a bool by showing that its square is equal to itself. We have that range 4 circuit from before. I use the bool circuit inside the range circuit, so you can define aliases with aliases inside them. Over here we have 3 different aliases that all use the same expression. We have q times y plus r equals x. This is just like the division algorithm. If you're familiar with div mod, you get a quotient and a remainder. This is that. By changing the signature only, we get 3 different aliases that have different outputs, but the same expressions. Expressions are exactly the same, and we are just selecting R, Q, or the pair QR as the canonical outputs for that circuit. Okay, this is the last slide that I'll really explain, and I'll kind of skip to the end. Here I'm defining, I'll explain what we're doing here. This is an example vampire circuit. The idea is it's a Pythagorean game, an educational game perhaps, where the player submits a triple, A, B, C, and also what their score they think should be. And if A, B, and C form a Pythagorean triple, then the player is granted a score of 1. Otherwise, they get a score of 0. So the player submits their triple and their expected score, and this can be done in zero knowledge. I don't know why, but it can. And the verifier checks that if a squared plus b squared equals c squared, then s had better be 1. And if it's not Pythagorean, then s is 0. All right, so here's the circuit that does this. I have 2 definitions. One is just for the Pythagorean equation, which, I mean, you can see it right there. And the other checks that x is, this gives you a bit that tells you if x is true or false. Right? So it's like a comparison operator that gives you a bit. All right. So once you define those, then the entire circuit, I know it's behind the couch here, but the entire circuit is on that bottom line. S equals is Pythagorean ABC. And that's the entire thing. That will end up being expanded out through a series of compilation steps, which I definitely don't have time for. But if you're curious about that, come talk to me. We have some promising directions with Vampire, and a couple of them I forgot to put on this slide. One is using algebraic geometry. Since a circuit also defines like a system of polynomial equations, you can use tools from algebraic geometry, ideals, varieties, and Grebner bases to analyze circuits to some extent. We've had some success and some failures with algebraic geometry, but it's really interesting stuff. Also, category theory. This is like very new, but we think we can compile a Cartesian closed category to polynomials, which will hopefully allow us to do some really cool stuff with Juvix compiling to Vampire. It's really interesting. Other promising directions, we are investigating using Vampire with Starks. That's promising, very new also. I think Brian Retford is here. I want to chat. And maybe like SMT solvers to help write circuits as well. Some really cool stuff. Finally, this is the Vampire team. We got some great folks working on it, people with compiler expertise. I'm really excited about the work that these guys are doing. It's great. So thank you. That's it.
Thank you, Joshua. Next, Alex Pruden. Oh, there we go. While Alex is going to give a presentation on the uniqueness of the Leo programming language. And while Alex gets set up, I have a program update. We're planning to have another talk with Anthony DiPrinzio from the Aleo team, but unfortunately we have to cut that. So, but Anthony's over there, so if you really want to chat about this with him, please go find him later. So after this talk, it's going to be the final talk today. We're going to have a break until 9, and then we're going to kickstart the panel that many of you are waiting for.
Okay. Perfect. Okay, hello again, everybody. I'm now here to talk to you about Aleo, so the shirt matches the talk. Again, I'm Alex, I'm the COO of Aleo, and I'm going to preface this talk by telling you that I'm going to talk about Leo, our programming language. And this is a high-level talk. The intention is not to be a deep dive into this. This is to talk about some of the features of Leo at a relatively high level. So if you expect this to be as good of a low-level deep dive into something like what Josh just talked about, I'm sorry to disappoint you. You should go get a drink right now and just enjoy that and watch or not. But anyway, I'm excited to tell you a little bit about Leo. So again, actually, okay, I guess before I tell you about Leo, I should tell you about Aleo. So, okay, Aleo, wearing the shirt, what is it? So Aleo is a new layer 1 blockchain, and the focus is on building basically just a platform for private applications based on ZKP. What is the advantage of doing this versus something like Ethereum? So Aleo runs on the research is called ZEXE, so zero-knowledge execution, was some research published several years ago that Howard co-authored, and he was up here a few minutes ago. And the idea is basically to take the Zcash model and extrapolate it to general programs, so not just simple payment transactions. So the advantage of this model, which I think Howard probably already talked about, so I'll run through these quickly, is program runtime can be unlimited. Effectively, you can prove something over however long you want and then submit that as a transaction. You're not limited by the block time of Ethereum. It's more efficient because you can prove something once, or you can prove something and then everyone just has to verify it once. They don't have to keep re-executing it over and over. And then you can kind of have a little bit of a flexible model in terms of how you want to execute a transaction. You can execute the proof yourself, or you can have a prover do it for you. And that enables you to have kind of like I say, a slightly more flexible model depending on the application. Again, the high-level idea, which I think applies to most projects building in ZK, which is one of the reasons why I'm excited there's so many projects building in this space, is that the goal is to take this from being a technology that only PhDs or smart people like Luke know how to use, and down to something where maybe even Alex, I can use. That'll probably never happen. But generally speaking, it's to make it so you don't need a PhD in cryptography to take advantage of this technology. Okay, cool. I'm going to skip this slide. This is basically, there's a lot of parts to Aleo. Today I'm going to talk about Leo, though, which is our domain-specific language and compiler. Again, this talk is going to be high level and relatively simplistic, almost offensively so I apologize in advance if that's going to bother anyone. But I'm going to start, so on that note, we're going to start talking about, okay, what is a programming language, right? So programming language is basically this is a method to write a high-level idea, and then translate that into a low-level program. That's basically what a language and compiler does for you, right? Just machines execute code, ones and zeros, right? And that's obviously a little bit cumbersome to work in or to think in. And so you need some high-level language that somewhat approximates English or something else to write the idea, and then you compile it down to the machine code. So this is a Solidity contract. I pulled this from SafeMath, the ubiquitous safe, or the ubiquitous library on Ethereum, and this is the bytecode, also from Safe Math, so I pulled this straight off of Etherscan. Little known fact that I'm going to reference later, so Solidity compiles down to EVM bytecode, so that's what the two blue boxes are. But the little known fact is that it actually, there's an intermediate representation called EUL that it can also target. And EUL is kind of a lower, it's not quite bytecode, but it's a lower level representation of these ideas. So it's closer to what the machine actually executes, but it's not quite as high level as Solidity. And so a lot of people use EUL because sometimes you can get more efficient by using that as opposed to Solidity. Okay, so high level language versus a low level language, the advantages and disadvantages. Again, this is quite high level. So high level language you can read, reason about, debug much more easily than something that's like machine code. A low level language is, because it's obviously what a machine basically operates in, is going to be more efficient generally, but not always, right? And this is where compiler architectures come in. And I'm not an engineer nor a compiler engineer by any stretch of the imagination, but good compilers can sometimes make it so that high-level languages can be fast as, or sometimes even faster than if you like hand wrote the machine code yourself. A good example of this is Rust, right? Where the Rust compiler can in some cases do optimizations to make it so that like had you even just written this yourself naively, it wouldn't quite be as performant. So that's why those are the question marks on the bottom there. Okay. What is a zero-knowledge proof? I'm looking around the room, and like half of you are like, I've been at this conference the whole time, and I've been waiting for someone to tell me this, and the other half of you are like, oh my God, I've heard this so many times, I'm going to throw up. And I'm not, so I'm gonna simplify this very greatly, and just for the purposes of this talk, just to tell you what you quickly need to know. So zero-knowledge proof, okay, so actually I just pulled a quote. I'm not even going to tell you, I'm going to have someone else tell you, right? So there's proof systems, right, which is like the context in which these proofs are generated. And effectively, these proof systems consist of polynomials, right, that are represented as field elements of a finite field. And these polynomials represent some kind of circuit, right? So the top picture is an elliptic curve, which is basically it's a group, and then this lower picture is a circuit representation of a program. The proof, so I kind of, the slide before, what is a zero-knowledge proof? So the proof itself is actually just, in the case of a pairing-based snark, is just a couple of group elements, curve points. And then the thing I wanted to highlight here, and this is a little bit of a side note or a little bit of a tangent, but some of you who may be kind of new to the space or new to zero knowledge are wondering like, why, hey, Aleo and Anoma building their own new blockchains, like, why can't we just do all this on Ethereum today? And the reason I showed this picture is because you can see like this elliptic curve and the circuit, like this is obviously like a different representation of a program than a typical computer would do. And Ethereum and the EVM is not really set up to encode programs in that way. So if you try and it's sort of like fitting a square peg into a round hole. So as a result, like encoding programs on the EVM potentially results in gigantic circuits because of like the underlying cryptographic constraints. So just something to highlight. Again, neither of these are my quotes. This is actually straight from a great article that I will reference at the end and share the link to. Okay, so now what is Aleo and what is Leo and how does this all fit together? So it's the high-level language, as we talked about in the beginning, is the idea for a program. So I want to prove that I know the sum of two numbers. I know it's a very silly example, but let's just go with it, right? And so you would basically convey that idea in Leo. You would write it, and then Leo itself would compiles down to the AVM, the intermediate representation. And the AVM does two things. The AVM is a layer that natively executes that logic, and so computes the answer, right? So you have to, in order to prove that the sum is equal to something, you have to actually compute it. So it does the native the program evaluation, and then it calls into SnarkVM, which is a lower level library in Aleo, and basically generates the program from which you can derive the proof. So that's how Leo, the AVM, proofs, and program evaluations fit together. And the important thing to highlight here is that as a developer on Aleo, you have the choice of whether you want to interact with Leo directly, so write in the high-level language, or go directly to the AVM and have lower-level control. So as I said, there can be advantages to doing it at a slightly lower level. It's slightly harder to debug and maybe reason about, but the advantage is you can generate proofs with less constraints potentially than you would, or programs with less constraints than if you were writing in Leo. And R1CS, for those of you who are not familiar, stands for Rank 1 Constraint System. And this is basically like the very low level representation of zero knowledge proofs. Cool. I have a couple slides about Leo. I think the thing I'm going to highlight here is one of the things that I'm really excited about is it's a language that we're formally verifying. And we feel this is very important because there may, actually, maybe I'll take a poll. Does anyone remember the bug in Zcash? There was a bug in Zcash. Okay. Okay. Zcash, for those, a couple of people remember, there was a bug that was discovered that would have enabled someone to mint an infinite number of Zcash. And it was discovered after the launch of the chain. And the thing that people kind of wondered was, well, did anyone ever take advantage of this bug? Well, because it was a private, it was a private cryptocurrency, you actually could never answer that question definitively. We think not, but because, private transactions, you actually have no idea whether or not someone did. And so the idea of formally verifying a language like Leo is to ensure that you're not, of course, you as a programmer can write a program with a bug in it, but a formal verification ensures that the compiler is not going to introduce a bug into your program that you wouldn't have otherwise expected. And I'm not going to get into formal verification in this talk, but it's something that not very many other languages have undergone, including in the traditional programming world. And again, something we feel very strongly about because, again, this contributes to the security of programs written on Aleo. Let me go back here. Yeah, the other thing we're trying to build with Leo, and this is a little bit separate from the AVM, is some kind of nice to haves that, frankly, I'm surprised more Web3 native programming languages don't include, which is stuff like testing frameworks, fuzzers, package registries, things that make the development experience easier on people who are familiar with programming in Rust or JavaScript or Python. So we're building all those in-house for Leo to hopefully make this as comfortable of an experience for a developer, particularly a developer who's used to coming from the web, the world of the web, and not the world of crypto. Because to us, the big opportunity is to onboard more web developers into the world of ZK and use that to grow basically the market of people, or the market for this technology. Cool. And so again, I think we highlighted earlier in the talk the difference between Leo and the AVM. But yeah, so this is just a quick summary about that. I think the key thing to highlight on this slide is that actually the on-chain representation of the program is the AVM bytecode. And so one of the unique things about Aleo compared to some other chains is that we have an on-chain basically namespace that maps program ID to program logic. And so that's what you reference as a prover. And actually, I think I have a slide on this. Yeah, perfect. So the way this AVM bytecode lives on chain, so you as a prover, you basically query the chain, get the bytecode corresponding to the program ID that you want to create a proof for, and you generate the proof. You can synthesize the proving key and verification key from those opcodes, generate the proof, wrap that proof in a transaction using Snark VM, and then transmit that transaction onto Snark OS, which is the blockchain. So you submit it to a node, and it propagates throughout the network. So that's basically the flow here for Aleo. And the other thing I want to highlight is that actually, as I mentioned earlier, the AVM can do both generate or synthesize the proof, but it also can handle native execution. And a mode that we're actually introducing in the future for Aleo is having this idea of a hybrid execution model. So for those of you who are familiar with the Zexi paper, it describes a model in which all of the computation is done off-chain, submitted as a transaction, and then verification is done on-chain. In this model, what we're contemplating is introducing basically a way, like we're thinking of calling it like a finalized statement, where you can write a program and have that program split into two parts. The part that you would prove off-chain, where a prover would prove entirely off-chain themselves, and then some logic that you want the miners or the validators on-chain to run, just like the Ethereum model. The advantage of this is that potentially you can manage applications that require concurrent state access more easily, right? So if you think about the most common example that comes up in this discussion is Uniswap. It's like, okay, how do you build a private Uniswap inside of a ZK Snark? Well, it's tricky because proofs by definition are generated by a single party, not a multi-party. It's not a multi-party computation protocol. And so you have this problem of like, okay, there's state that has to get concurrently updated over the course of a single block. So one way to do that is to basically, again, in our case, we have this effectively an EVM mode, which you can think of as a native execution of the AVM that validators execute directly, and it runs exactly like Ethereum. But alongside that, you can also have logic in the XC model too, and so you can maintain more privacy than you potentially could otherwise. And you can use this as a dial that you can basically decide how private or not private do we want this application to be. Because I think fundamentally in Aleo we believe that like not every application or not every use case needs full privacy. There are some that certainly do, but different applications and different use cases it may be kind of a middle ground. And so the idea is to give developers as much flexibility as possible to use to all the tools at their disposal to build whatever application fits their needs. The other thing I want to highlight is on top there. So we have Leo, like I mentioned, and that's what this talk has been mostly about. But the AVM is general, and we hope that as we continue to establish this and develop this intermediate representation, other people build languages or adapt other languages to target the AVM, and so give basically more ways to on-ramp into this ecosystem. Okay, before anyone gets mad at me for this slide, I didn't make this up, I pulled this from a talk from a YouTube channel you should all follow, which is the ZK Study Club, which I guess shameless plug, I help host with Anna Rose, the host of the ZK podcast. But this is from a talk by Alex Ozdemir at Stanford, comparing the various languages in the ZK space. So again, you take it from him, not me. And I guess like the key thing here is, Leo, we have support for primitive types. So, as I mentioned earlier, zero knowledge proofs consist of group elements and field elements, and that is not typically the way computers effectively work natively. And so it takes a little bit of extra effort to support primitive types, so we support those in Aleo. We let users define their own types, which is nice for a variety of use cases, array access, if statements, mutable variables, and again, as I mentioned, it's the only language, not only in ZK, but actually I think in general in the last 20 years that's actually been formally verified. Cool. Okay. What do we do with this? I'm sure this question's been answered many times throughout the day, but I'm going to give you my version. What's ZK for? Why do we care? Boiled down, these are the three things that I think are the killer use cases. So decentralized identity. My favorite example is the driver's license. Get into a bar proving you're 21 without showing your driver's license, because all the information on your driver's license is really irrelevant to the question of are you over 21, your address, for example. Shielded DeFi, which these days kind of extra important to prove you're solvent maybe without revealing your positions. I'm not going to name names here, but I think there's been a few large hedge funds and DeFi/CeFi firms that's been an issue for. But this would effectively let you have a proof to say like, okay, hey, I have a certain position or my portfolio has performed this well, but I don't need to show you or reveal its contents. So it's many applications in finance, to say nothing of the importance of being able to transact privately between parties. And then gaming. Gaming is a use case I'm extremely excited about. If any of you have not tried Dark Forest, you should absolutely do it. It's a really fun game based on zero knowledge proofs on Ethereum. Definitely worth checking out, and I think it opens up a whole new dimension of game mechanics that you can add on to and create basically a whole new class of games. And that's it. Thank you guys very much for listening to my talk.
Actually, Alex, before you run, we do have time for your questions. In case anyone wants to ask any, please raise your hand.
Anyone have any questions?
Yes.
I've already had a glass of wine, so I'll answer anything.
Okay.
Hi, thanks for the talk. I am curious about what it means, at least to you, for your language to be formally verified. I know a lot of programming languages researchers formally verify specific properties or theorems of the languages in Isabelle Hall or Coq or whatever. So I'm wondering what exactly it is that you mean by formally verified for Leo.
So since I'm not a formal verification expert, I'm going to defer you to Howard after this talk, and he can tell you. But the ACL2 is basically it's a theorem prover, so it's really the focus is really the theorem prover. So without embarrassing myself, that's as much as I'll say there, and I'll say after this talk, let's find Howard and we can chat about it. So like I said, not equipped to answer that question. Sorry.
Any other questions in the audience?
I even said I would answer anything, and you made me a liar on the first question.
All right. Thank you very much.
Thanks, everybody.
Cool. So we taking a break now until 9. So take this opportunity to hydrate yourself, stay hydrated, it's really warm. And then we'll be getting ready for the panel. The speakers will be arriving soon. Yeah. Everyone, I forgot to say, the bar is open. Please go grab drinks. We cannot waste those. Go nuts.
If blood will flow when flesh and steel are one, drying in the color of the evening sun, tomorrow's rain will wash the stains away, but something in our minds will always stay. On and on, the rain will fall. On and on, the rain will fall. Perhaps this final act was meant to clench a lifetime's argument. That nothing comes from violence, and nothing ever could. For all those born beneath an angry star, lest we forget how fragile we are. On and on, the rain will fall like tears from a star. On and on, the rain will see how fragile we are. Blood will flow when flesh and steel are one, drawing in the color of the evening sun. Tomorrow's rain will wash the stains away, but something in our minds will always stay. On and on, the rain will fall like tears from a star. On and on, the rain will see how fragile we are, how fragile, how fragile we are, how fragile we are, how fragile we are.
That's wonderful. I think it'd be a great idea if we gave you a full example of what's really going to take place tonight when Jazz and the Philharmonic unveils themselves to the stage Carnegie Hall audience.
what you get. An empty glass, an unmade bed, a picture window with a view. And all I think about is you. To feel so bad, to feel so good, to let it be misunderstood. Now I long to lose my senses and love you all over again. The shouted words, the tired sighs, the traded kiss of sad goodbyes, the living off of our desires, then putting out 1,000 fires. To feel so bad, to feel so good, to let it be misunderstood. Now I tear down my defenses to love you all over again. To know a place without regret. You make believe you paid your debt, but in that clean and quiet room, you can't believe it's over yet. Out on a log, at home asleep, the endings play, the bands retreat. But in that dumb luck of the few, the consolation comes to you. To feel so bad, to feel so good, the verdict's in, it's understood. I will be tried for my offenses and love you all over again. Out on a spree, at home asleep, the endings play, the bands retreat. But in that dumb luck of the few, my consolation becomes you. To feel so bad, to feel so good, the verdict's in, it's understood that I'll be tried for my offenses and love you all over again.
imaginative.
You're the king's temple, guarded by so-called and God's standards. These clay men had large eyes and boobs.
These unlike men had large eyes and store bodies.
Folded crane arms.
Fold trade arms. His big God.
Everyone will be starting in a few minutes. If you could start grabbing a seat or rush to grab your drink and then grab a seat.
They could stores of his house. Age. Shifted. We were told back then. Norman time. The newest bias were shown in high college.
We'll be starting soon with the panel. Panelists, can you all come close to the stage, please? Panelists. Justin, David, Brian, Howard, Christopher. So you go here, yeah. Howard, you go in between. David. Do they fit? Do you think they're gonna be comfortable?
What do you want to see? I'm flexible.
You guys think we need
So,
another chair? up here?
Georgios, you should go there. Same matches. And let me know if it's.
I can get another chair up here. if you guys
Howard,
want.
you should stay there.
No. Oh, it's 3 and 3.
It's okay. It's okay. Sorry if I said
Mics.
Okay. Just to be. Just
They're in order. They're matching. People can tell who we are.
So, at the bottom of the mics, there's a little button. Right here. So just shift one, and you guys should be live.
Test.
Test. Good.
1 2 1 2. Toast.
Tested.
Do you know what's yours? Okay. Amazing. So we're gonna kick off the panel. It's all yours.
Amazing. Thank you all for coming. My name is Georgios. I work at Paradigm, and we have a great set of guests today to talk about zero knowledge and other things. So maybe let's do a brief 1-minute intro from every person in the group, and then we can get started. Justin?
Yeah, I'm Justin Drake from the Ethereum Foundation, and I do research on future upgrades to Ethereum.
Yeah, I'm David Wong, and I work at O1 Labs on Mina cryptocurrency, and I'm also the author of real-world cryptography. And I used to do security for Libra and Diem, and yeah.
I'm Brian Retford. I work at Risk Zero, and we work on general-purpose zero-knowledge computation.
Hi, I'm Howard. I'm a co-founder of Aleo. It's a ZK-based blockchain, and I love cryptography.
I'm Christopher. I work on Anoma. I also previously worked on IBC. And at Anoma, I mostly do protocol architecture. And recently, I've been dabbling in compiler design. But I'm now terrified that someone who clearly knows more about compiler design than I do is sitting 2 hops away. So I'll try and not say anything that's too terribly wrong. But if I do, at least I'll learn something.
Amazing. People kept the intros to 1 minute. Impressive. So maybe we can start by defining things, because the presentation's about hard problems in decentralized systems, but what is a hard problem in decentralized systems? And I don't have any specific person to take it, but if anyone has strong opinions, should go first. Okay, maybe Justin, you go first.
There are no hard problems in the sense that everything can be solved in theory. At least that's the optimistic approach that I take. And like my philosophy to doing research is that tends to be an easy solution, like some sort of proof of existence. And oftentimes it doesn't use cryptography. Oftentimes you use incentives as your other tool in the tool stack. But what you want to do long term is try and remove these rational actors, because they're very difficult to model, and you kind of want to replace them by pure mathematics. And then the difficulty becomes, do we have the cryptographic primitives that we want in theory? And often the answer is yes, because in theory we have obfuscation. And then the next step is, can we have something practical? And this is where we spend 90% of the time.
Going from theory to application and making it easy to deploy, perhaps, would be another way to put it.
Yeah, and I guess in that sense, you can think of blockchains as being machines that transform pure cryptography to real-world cryptography.
So I think that's one angle. I also think that we have a lot of people in this room that take different approaches, depending on the project that you work on. So I wonder, for example, Chris, what's one hard problem for you?
What's one hard problem? To be honest, I might surprise you, but I
One.
actually agree with just one. Okay, there are no hard problems in theory, only in practice, and only in practice in time. We're just ordering events in time, what's a hard problem? To me, at least recently, I'm going to say compiler design, because I feel like we have all of these different systems for privacy in different ways, and basically no way yet for people to write applications in which they can reason about the privacy of data. And that programming model is just completely different. It's like distributed programming. There are agents, there are users, there are blockchains, they're all interoperating together. The whole thing is really complicated. And we're currently approaching it from this I'll build my blockchain or my bridge or my roll-up angle. No one sees the whole thing. And I think this is it's just a sort of different complex system, and until we get a good language to frame that different complex system, we're not really going to be able to understand how it behaves or use it safely.
Got it. This is a privacy event, so I'm surprised that 2 questions in we haven't heard about privacy itself being hard. So I wonder, is it hard? How hard?
Well, could I say, does humans count as a hard problem, or?
Oh yeah.
But no, to be frank, I think the privacy topic is a very hard one. Why? Because one, getting state on chain, getting it private, and then accessing it, getting it to the right parties, as Chris has mentioned, is there's a UI UX challenge, but there's also a significant performance challenge. I think also, and this was something that was discussed earlier today, it's just being able to create a user experience in Web3 that looks like Web 2, but can do more than just Web 2 does and gives you self-sovereignty is a crazy tall order of an ask. You want the cake and the cherry and you want to eat it, And so I think that's where we are today with a lot of the ZK solutions is you can actually do that, but you're going to pay a lot for it, and that's the trade-off. It's well, maybe I don't want the cherry, and it'll be cheaper, but then at some point you start to degrade and make compromises where you end up leaking your metadata. The problem is that especially as we are moving and bridging between systems and using ZK to do bridges, you can get this type of state from third-party sources, from third-party apps. You can then cross-link and immediately start to de-anonymize people. And so there's a lot of risks involved in this design, and you kind of need silver bullets to make it work. And frankly, privacy is a fundamentally hard problem then.
Maybe to regurgitate, privacy is hard because you need to do everything locally, because the moment that you outsource something, your privacy is obviously lost.
Yeah.
Even if you do it locally, you still have humans in the loop that maybe don't care about privacy, don't know anything about privacy, don't understand that they might do something that they think is private, then go do something else somewhere adjacent, and then all of a sudden they've just made their last private transaction completely open now.
And even more so, maybe you want multiple parties to interact together to do something, and you need to keep it private for everybody else outside of this small set of people. Good luck.
So if I can add also, something that we don't really talk about when we talk about privacy is how we can reconcile also the crypto world with the current financial world, or the traditional finance world. So actually, I just came back from the CFF, I think the Crypto Finance Forum, and everybody there talks about cryptocurrencies like there's no privacy, and it's this black box that you can regulate by regulating the service providers, but nobody really thinks about the L1s and how you can like maybe find privacy solutions that can be integrated at the L1 and also be regulation friendly, and actually, I don't know, make crypto, this thing that people can use at a massive scale.
Yeah, I think ZK in particular can really potentially help with people's regulatory concerns. I have this vision of this world where regulators can come up with sort of regulatory bots that get approved by some kind of oversight, ideally civilian citizen operated oversight board, and then these bots can run in a ZK context over private data, but they only emit data that's proven to not compromise privacy. I don't know. It's like a weird world that's very far from now, but it seems possible with ZK to actually
maybe
bridge that gap.
Zooming out a bit, we are designers, engineers, or system designers, but in the end, you have a toolkit. The toolkit, you open it, it has a bunch of different tools. You just mentioned ZK. How does designers' toolkit look like for people that try to shift away from incentives to more, let's say, strict mathematical methods? You said ZK snarks, and so on, but it can't be just it. So I wonder if you guys have any input on alternative methods beyond just snarks. And snarks is a good answer also.
So I think one of the trade-offs that gets made, especially when you start to generalize and abstract concepts, is that you always make a trade-off in terms of efficiency versus usability, right? So in our particular case here in this domain, you either can go straight to the math and you can come up with solutions that are expressive and performant, or you can start to black box things, but you start to make compromises at each level in order to make it more humane or humanly usable for people who are less knowledgeable. And I think that there is a universe where you can very, very special tailor it to be very efficient and still be general purpose, but that requires a lot of engineering effort to go into it. So I think at least within this domain space, there's a very kind of clear XY axis of what you're trying to achieve, and you're trying to linear regress into that to try to find where along that sliding scale you want to sit. But I think that in broader terms, that if you want to design a solution that can also address privacy, frankly, ZK is not the only one out there. We've also seen, there are secure enclave approaches. There's MPC-based approaches beyond just snarks.
Do you want to paint a picture on you said an XY axis or some sort of trade-off space? How does that look like across techniques?
I think people think of all of these tools, ZK was, not even something people really conceived of as even possible until 7 years ago or something. And homomorphic encryption is only barely possible now. And MPC is still, people are making a lot of advances in all of these areas. And the thing that I think about is that each of these cryptographic tools lets us solve very difficult problems or approach them in ways that we haven't necessarily thought of. And they can work in concert to Aleo uses formal methods and ZK together, right? So formal methods, ZK, HE, MPC, all together, the class of problems that we can solve that we don't assume we know how to solve, I think it creates this huge open space. We have to revisit all of the assumptions that have gone into distributed system design and human systems now that we have these kind of incredibly powerful new cryptographic primitives.
Yeah, I'm personally very bullish on the MPC plus ZK. I don't think that's been very explored actually, unless we're talking about ceremonies or these kind of things. But yeah, ZK and MPC I think has a...
Maybe just double click on that. What does MPC plus ZK mean? Because in my mind, MPC, I have 10 parties and I say at least 6 of them need to do some kind of computation correctly, and that computation happens in an encrypted way, and nobody learns anything about that computation. That's one thing. And when I hear ZK, I think snarks, which does not involve many parties. So what does that mean?
I always think... Oh, go ahead. Go for it.
One possible interpretation is that actually ZK is a building block to build other primitives. And so in MPC protocols, oftentimes, you want parties to behave in a very constrained way, and so they can make a proof that they are participating in this constrained way. We're using, for example, snarks in VDFs as well. And there's many other primitives that they go alongside with. So for example, with fully homomorphic encryption, you kind of want to prove that you've advanced the state, the encrypted payload according to some very constrained things, and you can use a snark that accompanies the FHE as well.
This, just to add on that, this specific way of using ZK as part of other protocols, I think my favorite application was in the context of Schnorr signatures for Bitcoin, where typically, like, nobody cares about Bitcoin, unfortunately, and yeah, but like, I still pay attention. It's pretty good. Like
you're at an Ethereum conference talking about
yeah,
Bitcoin.
right.
Sorry, man.
But like typically in Schnorr signatures, you have many rounds, and parties need to interact within this round to run the protocol securely. But by adding a ZK on the first part of the protocol, which is the common nonce generation step for people that are familiar with threshold signatures, you can avoid the interactivity step. So you can almost use it like a spice on top of your normal protocols to remove complexity.
Yeah, I think Dan Bonnet, he was just telling, when we were at Stanford, mentioning they had some protocol that used snarks to make MPC much more efficient. I haven't actually read the paper, but I've been meaning to, so like, definitely. I also personally find ZK and HE versus MPC to be kind of the same thing, but I don't quite, MPC lets you do computations in a way where nobody ever needs to know the data, but yeah.
Yeah, I mean, I think there's definitely a complement when it comes to ZKPs and FHEs, because the zero knowledge proofs ensure you get data privacy, so then the contents of what you put into the program are hidden. But the FHE part allows you to actually hide the logic behind what was also going on there. And the ZK case, the circuit itself must be known to both the prover and the verifier, because they need to be able to derive this key and make sure it's the right key. And so in this particular instance, the marriage between the two actually allows you to do some pretty cool stuff. And so if I want to just even update balances, numbers, right? I can do a very basic partial homomorphic encryption where I'm literally just multiplying two group elements, but their exponents could be addition or subtraction. I might not know, because in ZK I made sure it was obfuscated already, the values. And so I don't know, was I incrementing? Was I decrementing? Am I going up in terms of the reserve amount in Uniswap, or am I going down? I wouldn't know necessarily just from that alone. But there's obviously a huge domain of practicality that are challenges in that. But yeah, I do think on the MPC and ZK front, originally when you said that, David, I thought you were thinking maybe threshold encryption or stuff like that, where on the ZK front you want to kind of accompany the fact that there exists a stateful chain where you want to threshold decrypt or threshold encrypt state.
Or you can do pretty much everything you want. But there's this paper from Dan Bonnet, I guess, and someone else. Sorry. Who
There's always a Dan Bonnet paper.
It's always Dan.
And I don't think it's the first author, so I apologize. But that explains how to pretty much create a zero knowledge proof as a group of people where different people know different secret inputs.
Yeah.
And so yeah, I feel like the sky is kind of the limit with that. What can we do with that is kind of up to you after. Yeah, maybe you can update so you mentioned that homomorphic encryption to update something. I don't know if you guys know about CryptDB. It's a database encryption system where it's pretty old, and it's one of the only systems that uses homomorphic encryption that I know of at the time. Maybe today there's more, but I don't think so. But yeah, you couldn't know what update they actually did. You knew that they updated the encrypted value, but how they updated the encrypted value, you have no insurance. So that's interesting.
Right. I mean, I think the practical synergies come into play a lot where they make certain kinds of applications that you want possible now only when you use multiple primitives, because some of them are too efficient. The ones which can theoretically do all the things are too inefficient, but if you split it up, it works. So in our case, we're trying to do private bridges with fault isolation, and for fault isolation, you need to measure aggregates. So you need partially homomorphic encryption plus some MPC plus zero knowledge for the actual transfers.
So, sorry, Chris, that was a lot of words.
A lot of buzzwords.
Can you dumb it down 10 levels? Like you said, FHE,
Yeah, so in the IBC security model, right, we want to provide fault isolation.
Nobody knows what
Okay. Multiple blockchains, different validators. I trust my validators. I don't trust Justin. Justin's like the other validators, right? Say David over there wants to send some tokens from my blockchain to Justin's blockchain, and Howard wants to also use some tokens on my blockchain, but he like also doesn't trust Justin's blockchain because Justin's sitting all the way over there.
Whereas in the current IBC model, each chain needs to trust each other that it's secure.
No. In the current IBC model, these chains keep accounts for each other, and they measure how many tokens go over to Justin's chain and come back. And if David sends some tokens over to Justin's chain, then Justin is Byzantine, and Justin goes and steals them. Then David can send, or someone can send those tokens back, but they can't send more tokens back. So Howard here is protected from inflation.
And where does the ZK part come in?
Because this requires a counter. It requires a counter across user transactions. So even if you have compatible like sapling systems on both sides, compatible private transfer, zero knowledge private transfer circuits, you need, in order to provide this fault isolation, you need to measure an aggregate.
So you're saying fault what?
In order to provide fault isolation.
Isolation.
So, you need to make sure that Justin's chain doesn't send back more than he was originally sent. And in IBC, this is just done with a transparent counter because the transfers are public. It's easy. And you can maybe choose to hide some identities, but keep the transfers public in a bridge and get this. But if you want everything to be private, you need a homomorphically encrypted counter. So there's a near-term example of something that I think is interesting.
Zooming out, I think everyone here is building some kind of product, and I'm curious, because this is a privacy event after all, what are the most applicable techniques that enable you to build privacy-related products? And let's start from that, and I have some follow-ups. Which is the most important technique to use for private applications?
Hash functions. No one said that ZK integrates well with hash functions because it's so obvious that no one needed to say it. But if we didn't have hash functions, we would have nothing.
I thought everything is a Merkle tree, and we already concluded this in a previous panel, years ago. But no, I think that in general, encryption is also just such a vital part for privacy, right? And it's so intrinsic and it's almost assumed, but people haven't really thought deeply about threshold encryption, threshold decryption, and then also about selectively disclosing state and revealing state. I think that in terms of building applications, you want to build, if you want a voting system, or if you want an auction, there are points where you want to disclose for auditors, or in general to reveal just the final bid, for example, but not all the prior bids. You want to be able to do this flexibly, and that is a hard problem to build efficiently and make general purpose. If you just create a special tailored circuit, I think it's very, very well doable. But again, the primitives that you're using here are today mostly either very inefficient traditional classical crypto, bit-based crypto, or you have very unproven new field-based crypto that is generally conjectured to be right and has collision resistance, is a random oracle, etc. But it does not necessarily. We don't know yet. It's also very early.
I want to hear from Justin here. In the context of the Ethereum roadmap, where does cryptography and privacy play an important role? Not necessarily today, but not 5 years either. So let's say in the next 2 years.
Right. So I guess there's two places. One is the trivial signatures, right? These are a special case of privacy where you don't leak your private key. But the more interesting one, I guess, is secret leader election. And the idea of secret leader election is that you don't know who will be the next leader. And we actually just use a zero-knowledge proof of permutation. And
why is it important to not know the next leader?
It's important because otherwise you can find the IP address of the next proposer and you can DDoS them. And that means that they don't get to produce a block. And that's especially bad because of MEV. The next block builder gets all the MEV from the previous block.
What is MEV?
It's essentially transaction fees, yeah.
Okay. But my understanding was that, at least in the Cosmos ecosystem, it is very classic, and we've had the discussion before, that people have a signing node, and they put a bunch of sentry nodes around it, so DDoS is not really an issue anytime, because you just put a bunch of protective nodes around your signer, so why does it matter?
Right, so if you only have 100 validators, then they're each industrial grade, operators, then they will have the network infrastructure to protect against the DDoS attacks. But if you have 400,000 validators, a bunch of which are running from home, they won't have this infrastructure.
Okay, so we're using privacy as a way to make, let's say, at-home validators more resilient attacks.
Yeah, and I guess the other thing to mention in terms of privacy is like, from the context of MEV, I think the long-term solution is encrypted mempools, and the idea here is that you have this ephemeral encryption of transactions from the point where of the origination of the transaction from the user and inclusion on chain, and then once it's included on chain, it gets automatically decrypted, and that could be using threshold decryption, or it could be using time-based cryptography.
Chris, like you're doing that, right?
We're trying, yeah. I mean, I wasn't just trying to include buzzwords. It's actually that like the combination of those three things, like partially homomorphic encryption for the addition, and a little bit of MPC for the like non-negative test, is what makes this, we think, might make this practical in the short term. And I'm hoping that that's a technique which can be, at least as long as we lived in this bridged ecosystem of many rollups or many different security domains in some sense, many different blockchains. I'm hoping that we can collaborate on standards that allow that to happen, because it does require agreement. Like agreement at the edges of zero-knowledge protocols is currently not happening at all, because everyone's using different proof systems and different curves and different languages and different like architectures. It's like fragmentation, which is great for development, but at some point I think it also has to converge.
Winners set the standard, I think. Like it's a big space, the pie is big, high competition.
This is why we have a 256-bit VM, cough cough. Just kidding.
A bit more opinionated, but I would say that arguing about VMs is not in scope. Like asking David and Howard, who are, I think, the private application builders here, what are the challenges towards building a private application? And are there any fundamental trade-offs in terms of UX, performance, complexity, and so on?
I think one of the biggest challenges is managing off-chain state. I think it's one of the most overlooked things that, especially from the academic space, it's considered an engineering problem and it'll be solved. I think it's a crazy, unexplored territory.
Can you unpack why that is a problem?
So just for ETH devs coming in on a high level, like, what am I saying? Like, normally from, as an ETH dev myself, like, normally you think about all of your state living on-chain in this, kind of, there's like a virtual cloud, right? Like where everything lives there, you just call stuff, transactions go there, and then the network executes it for you, right? In the ZK universe of things, when you want to have privacy, at least today, the way that it typically works is there may be state on-chain, but separately, I need to execute off-chain. The VM does not live on-chain. It executes off-chain. I do off-chain state management on that. I need to, for example, if I want to prove a Merkle path, the Merkle tree might exist on-chain. I can go fetch a path and then go put it in here. But also that I may also have like private tokens with private state, and I want Merkleized trees off-chain as well. Those trees can get very large. Either I keep it in memory or I want to go and synthesize new things. Separately, if you want to then add visibility and view keys to that, because you're a normal company and you have engineers that are low level, some are senior, you have a fraud department, maybe only some people are supposed to see it, others aren't. You then have to now reason about access control on this front. And there's a lot of extra nuance that gets introduced because of privacy. Like when it's all public, there's no access controls. Everything can live on chain. The network can even manage it for you. It ends up being kind of fairly straightforward of a toy example in that universe. But when you start to get real about it, it can get very difficult on the state management part.
Let me just play devil's advocate on this. That Tornado Cash is a trivial example of this, where you store some secret to your deposit, and a very reasonable solution is that you encrypt that secret with your private key. You store that encrypted thing somewhere in a cloud, in a chain, whatever, and you can always access it. So why is that not tractable as a problem?
So think about it this way. If I just encrypted it using my private key, which seems like the natural motivator, the problem is that the network can't verify that the state that it's going to host is actually the right state, because like this is something that can be, it's called the Fairygold attack in Zcash, right? Like I can send you a note and say like, look, I sent you $5, like you can go spend it. But the problem is that if I sent you the wrong ciphertext for it, you still can't spend it. I can even show you that it exists, but if you can't decrypt it and use it, this is a usability issue. And then when you get into the application state of things, let's say you're playing a game of chess and you can tell, I'm going to be checkmated next. I don't want to go pay. I don't want to win, or sorry, lose. I know he's going to win. In this case, I may not want it, but I'm obligated to go and play out the game via the protocol. In this case, I can then deny the actual payment at the end of it, and these can become real issues in terms of UI UX and also the expectations of a protocol. You can break protocols. Let's not get into DeFi risks on that front. But the idea is that like there ends up being a need to then say I need verifiable encryption. If I need verifiable encryption, all of a sudden this says, all right, So then I need it to be an asymmetric key system. So that means that my address is what I'm going to encrypt under, and then I'm going to decrypt using my private key. If I do that, now this key pair not only does signing, it also does encryption, which is another layer of assumptions. And frankly, it's a large cost to make on that. But then separately, I also need to then, in zero knowledge, prove that I encrypted the thing correctly. There's just multiple layers of complexity that get added on. It becomes the challenge.
So if I can add on that, so I agree that where do you put the data is like a problem, or not actually. So I would say that maybe it's not a problem. Maybe we don't care. Maybe we can accept the fact that applications today like have some data somewhere, and you actually don't really know where the data is, and that's fine as long as they can actually show you that they did the thing correctly using zero knowledge proof, for example, and maybe roll up from time to time. Then it's fine. The other thing I'm interested in is like Celestia. So if you've heard of it, it sounds like a good solution for this kind of applications, where you. So if I understand correctly, how Celestia works is like in your ZK app, I guess you'll have something that verifies that you actually posted your data on Celestia, so that you can use it. And for that to verify, it's basically a consensus, a BFT consensus there, and you have to verify a bunch of signatures, and everything is fine. And then Celestia has to like deal with how they preserve data forever, how they serve data, and everything like that. But it's basically none of your problem if you're a layer one.
But Celestia's DA proofs are interactive, right? So wouldn't users have to verify them?
Sorry, what?
They don't have. You can't have non-interactive data availability proofs. So how would
You can.
You can.
KZG data availability. You know it better.
Oh, okay.
I mean, you're just verifying a bunch of signatures. That's how you verify that data was posted on chain. So basically, they have a consensus, it commits, and a commit is 12 plus 1 signatures. It's a BFT thing. And so it's basically like a light client, where you can verify that it's part of the state of the Celestia blockchain because it was committed there, if that makes sense.
But you're trusting
Celestia
to
store the data.
To store it, yeah. So you're just breaking trust.
It's like a
right?
signature from, okay.
You have something to say about
Just to clarify, so it's not like a chain doing data availability sampling on another chain. That's not possible. It's just a committee basically vouching. Yeah.
But I think I can see a future where like every ZK application built on a blockchain is actually some sort of roll-up. And so you don't really care where the data is. Like it's anybody can do whatever they want basically, as long as the things are verified when they come back to the when they settle on the L1, then it's fine.
Yeah.
So maybe it's not that big of a problem. Yeah.
This is a good segue to the next question, which is like for you, Brian, which is what about scaling? ZK rollups are systems that have gained a lot of popularity. They're called ZK rollups, but they're not really zero knowledge in the privacy sense. So what's up? And then I have a follow-up question on virtual machines, which you also have a lot to say.
Yeah, I mean, I think the MEV question is interesting to me. Like, people worry a lot about MEV, which is, letting anybody decide what order transactions happen in. And to me, even the notion that transactions have a particular order or need to have a particular order is kind of broken. Like, if you can prove that a transaction, a state transition is actually okay, and that some giant set of them don't conflict, and you can do this in a ZK way, then you can kind of just roll everything up in a effectively non-ordered manner, and really to get past, if we really want to build a world computer that scales, you can't order every transaction. You're fundamentally rate limited if you order every transaction. So in my mind, as soon as we achieve scaling by doing some kind of parallel tree
just interrupt. I think the MEV scope, I think, is like a bit like later. I think even before that, like why is a ZK rollup important, and how does it work, and how does that line up with the risk zero context? And we can talk about MEV and ordering, etc. in a bit.
But, I mean, by the way, on what you were saying, I guess some blockchains are already doing that. Like if you look at Sway from Easton Labs, so if basically payments, you don't need to order payments, or for like some use cases, you don't need to order things. So you have protocols like FastPay where you can just do everything in parallel, basically.
I mean, go ahead. Yeah.
Yeah, and in the context where you have encrypted mempools, like every transaction is can be commuted with any other transaction because you have no knowledge of Yeah.
Right.
And so,
Yeah.
but there's still going to be like maybe like 1% or 5% of transactions which will be order dependent, in particular like arbitrage and whatnot. That should go at the top.
But I think, yeah, for just the easiest way I think to think about like, you know, why ZK is really impactful to scaling is like you can take any computation that you used to do on chain, effectively do an arbitrarily long computation off chain, and just post a very succinct notion of it somewhere, and that can be rolled up, you know, as many times as you want to. But effectively, it lets you move everything off of a model where people have to repeat any computation more than once. You don't have to vote on whether something, you know, is secure anymore. You can just prove anywhere on client that it happened correctly.
What's the design space? So, okay, doing ZK or validity proofs for payments, we get it, it's easy. How do you do smarter things? So you also have thoughts on zero-knowledge VMs, but I want to hear from you first because you do it in the transparent context initially, and then we can talk about the ZK context. So risk zero, you take a risk 5 architecture, you somehow convert it to a AIR and R1CS. Now I'm saying words. But like, what are the challenges towards building something like that?
Towards building
a virtual machine that's verifiable.
Yeah, I mean, you know, to some extent, you know, Fry kind of, I guess, solved that. It's, you know, Fry's slow, and there's certainly like a lot of engineering challenges, but I think the math was kind of settled before we even, you know, started this company. So the challenges to building a virtual machine are just kind of, I guess, believing that you can do it, reading enough math, and then using the right like mathematical tools to you know, use a circuit system that will actually let you encode a complete like machine architecture as a circuit, because it's really just a circuit. The circuit is.
I mean, everything is a circuit, but if the circuit is 2 to the 30 constraints, it's gonna take a ton of time to prove. So I guess the question is, under limited resources, how do you get to a system that's expressive enough while also being?
Yeah, I mean, that's one of the reasons we chose the RISC-V architectures, because that just doesn't have.
So the question is why?
Yeah, you get away with like 132 constraints or something to represent all of the instructions, and I think once we move to lookup, it's going to be a much.
What is lookup?
That's a question for cryptography engineers that I'm not one of, but somebody else can explain it better than me, I'm sure.
I think the high-level way to explain it so that it's interpretable is you can create custom gates and use a lookup table that has indices, columns of data. So, you know, maybe let's say you have a key value store, and I can look up values with them. I can use custom gates to enforce those lookups, and then I can check them. Why is this interesting? Because normally when you do computations in a circuit, it ends up being very expensive to mimic traditional like bit-based systems, Boolean-based systems. And so by having lookup tables, I can fast track or skip a lot of the computations that otherwise I would have to actually manually compute in the circuit. And so, like, if I'm saying, like...
I think as an example, like the XOR table is a good example.
An XOR table is a great
Or
example.
even for, like, range checks, you can, like, just have all the numbers from 0 to, like, some value and just check if it's in that table.
Yeah, I think like 70% of our circuit is just bitwise operations, because you have to do it every bit by bit by bit by bit as separate constraints.
Maybe for the crowd, the simplest way to explain lookups is that computation is expensive to do, so you pre-compute it and you just show, you know, when this input comes, use this output instead of running the computation over and over. So it's a classic pre-computation, pre-processing optimization. It's like caching almost, where you cache it.
And then done and enforce using math. So
yeah,
it's always
you enforce that the
magical
cache
math.
is correctly looked up in the circuit.
You basically have an equation where left-hand side must equal right-hand side, where left-hand side looks different from right-hand side. Left-hand side has some of the actual data. Right-hand side has the expected data. You want to make sure they match each other. And then you just create these like mathematical, like polynomial terms to like basically clamp it down so that you could only have possibly put the right values there. You could not have put any other values in the terms such that the right-hand side would equal left-hand side.
Oh, and you can also do more. Like, so Kimchi, the proof system of Mina, we have runtime tables now, so you can use lookup tables to like, as like a memory access where you can write and read from, so pretty cool.
The pre-computation techniques and lookups, honestly, I think is super still underexplored, because there's like a bajillion things you can do, and also it's very much an art, because the question is like you always have a time and space trade-off. I can fast track a little bit more, but I need a bigger table to do it, or I need to choose the right things to put in the table to make it faster, and there's no real algorithmic science or precision, like I can quantitatively say this is the best. There's a lot of an art to trying to find what is the best.
That's really, and as Chris was saying earlier, this is where we're starting to really get into the realm of like what we traditionally think of compilers as being responsible for, right? It's like making these very like thresholdy optimization decisions using heuristics or using AI. There's all kinds of different techniques, right? But you see with all of these crypto, like every new technique somebody invents for ZK is basically another, set of compiler passes that we as collectively kind of need to be able to optimize things well.
I can't wait for the next wave, which is going to be ZK compiler using stochastic gradient descent and simulated annealing to find the optimal lookup tables. Like, there's going to be buzzwords on this.
You can make it the longest buzzword.
We try to keep it low buzzwords. I agree. Okay, so we have a RISC-V VM, we have a custom VM, we have another custom VM. Is a ZK VM real? Is the meme? We had 2 announcements today of the first ZK VM ever. So I wonder, is it a tractable problem? Are the approaches that exist today, you think they're long-term ones? Is the research project? And if it's too much opinion. What's that?
3 announcements of ZK EVM.
Yeah.
I think there were 3.
I lost track.
Maybe 4 tomorrow.
Yeah.
I think one of the Celestia guys has a really funny tweet about that. But
I saw that.
No, it's very tractable. I mean, the RISC Zero VM works fine today, and you can, in fact, if you try hard enough, run other VMs on top of it. So I don't think I think the debate as to whether VMs are possible is completely over. Whether they make sense in any particular problem domain is a completely separate question, though.
So this is a good train of thought. Before we get to that, because it's where you take EVM and you compile the RISC-V and then you run the RISC-V in the start, we can talk about it in 1 second. But there's a kind of question of, is building a native ZK VM better or one that is kind of emulated?
So people are arguing today on the definition of a ZK VM, and just to add a bit of spice, I think they're all wrong. And the real definition of a ZK VM is one that is state root equivalent. So it's a virtual machine that produces exactly the same state root. And this is the long-term goal for Ethereum, where we want to snarkify the canonical instance of the EVM and create a so-called enshrined ZK VM.
What does enshrine mean?
Enshrined means that it benefits from certain advantages from integration with layer 1. So for example, if we need to update the EVM, well, the social layer has the credibility to go update the rules of the EVM just like we do hard forks today, whereas we won't do interventions at the smart contract layer. Now there's various relaxations of from this very strict definition of a state root equivalent EVM, and it's basically a bit of a spectrum. So the next best thing is bytecode equivalent VM. And then you may have some sort of language level VM where you're compatible with Solidity, but then you have this compiler step. And even within these categories, you have different variations. So for example, Hermes has this constraint where every transaction can't use too much gas. So it's kind of an additional constraint on transactions, but Scroll is like slightly more bytecode equivalent because it doesn't have this constraint.
But there is some trade-off, surely.
Yeah. So there's big trade-off space here. Like one is time to market. Like if you design a very simple VM, then you can access the market much sooner, but maybe you won't be compatible with all the tools, and so you have less network effects. There's also trade-offs in terms of security. So if you have a very compliant circuit to the VM, it's going to be a very complex circuit which could have bugs. On the other hand, if you're doing a language level EVM, then you might have bugs in the compiler. But then it's kind of interesting because what if there's a bug in the compiler? Does it mean that all contracts will break? Probably not. Only just some subset of contracts will break. Whereas if you have a bug in the circuit, that means that the whole roll-up could be drained from one day to another. And actually, my prediction is that we're going to see roughly half of the ZK rollups just get drained from one day to another, similarly to how we're seeing bridge hacks happening today.
What's the market structure? What's the split between techniques, you think?
You mean of the different approaches? people are trying like the whole spectrum.
2 years from now, how do you see it? Like, what percentage of the market is EVM compiled to RISC-V running the RISC-V VM versus, and you will say 100%.
I mean, I wouldn't go that far, but I do think, Justin's pointing out some important factors, like actually building, if you look at the Hermes announcement, you look at how many of the ETH tests are actually passing, it's not very many of them, right? And so by the time you build a circuit complex enough to actually pass all those tests, can you be certain there are no bugs in that? Like, what's the audit of that going to look like? Unless you build it with like Aleo, and then you're certain that the compiler spits it out, and then you have a nice, like, formal spec for the EVM.
What's unique about Aleo?
So personally speaking, like one of the big challenges that I have at least experienced, and it's why we ended up going with a ZK VM, basically, like not a ZK EVM, but just a ZK VM, is that the compatibility to an existing system that was not designed to be like snark friendly at the get-go, some parts are, not all, is that you end up paying for these extra costs that otherwise would be very cheap. And a lot of this, underlies the curve that you sit on. It underlies the types of hash functions that are used, that are native. And frankly, like, I'm very excited to see these ZK VMs that are coming out, because I think that they're actually going to, one, shed light on, what is possible and what is hard. And I think that that's going to create a new set of research problems for the next group of people to also go and solve. So there's a huge amount of utility in that. I'd actually be frank in saying I think one of the biggest challenges that's probably not spoken about in these designs is likely the version control in these compilers. Because as you know, with zero-knowledge proofs, every time you synthesize a proving key and verifying key, if you change one opcode or even change one gate, the PK and VK are no longer valid. And if you want to keep that one-to-one with Ethereum's development, you'll need to have very good version control to make that actually work.
Key management problem.
A proving key,
It's
verifying
still not
key
solved.
management, yeah.
I mean, yeah, but you need to distribute.
And I think that one of the biggest challenges in getting that right is also that you need to keep those keys statefully available and in real-time update and use them, because these keys are massive. Like, for small statements, they can be 100 megabytes. For large statements, they can be gigabytes.
Can it not be a consensus parameter?
So it would be a consensus problem if one set of group of people have the right verifying key, the other set does not have the right verifying key, and they disagree. You can fork a network this way.
I guess what I'm saying is that you make the validators of the chain agree on the PK/VK.
Yes, you would need to agree. You need to reach consensus, and basically, like you also create potentially disincentives if there's a set of validators who are not ZK friendly and a set of validators who are provers. And they disagree on a specific spec change. It's a people problem at the end of the day. But
I think it devolves into governance pretty quickly, just like but it's a very real problem.
The mechanism, in order to get that to work, requires at least a process, which I have yet to really see in these designs, to make sure that transitioning between these design changes, even if there's one gate, because I guarantee you, every one of these circuits has some bug in it. We're humans. We make mistakes. It's natural.
Do the Aleo circuits have?
What's up?
Do your circuits?
Yes, with ours too. I will be the first to admit. And by the way, we have a bug bounty coming out in phase 2 of the testnet 3 announcement that we did earlier.
No marketing, Howard.
Yeah.
Okay, we have 9 minutes. I want to go around the panel and then ask questions from the crowd. But for you guys, one by one, what's one problem or open question that you're working on or you want more people's eyes on other than the bug bounty?
What VM layer should we standardize applications at? I think this choice really matters. We can standardize applications at a very low layer, and that means we're not so vulnerable to compiler bugs. At least they'll be isolated to specific applications. Depending on how simple or complex the low-level layer is, that's like thing that has to be verified. On the other hand, we can standardize applications at a higher layer, which gives us the ability to make compiler optimizations without breaking consensus all of the time, and maybe provides an easier path to dispute resolution if things go wrong, and is easier for interop. And I don't know, there's a huge complexity of trade-offs there.
I think one of the things which by the way, that's why I really like Vampire, is I think that there is...
Sorry, what's Vampire?
So Vampire, which was from a previous talk, is basically a standard format of representing constraints that allows you to easily translate between different domain-specific...
but it doesn't do well with custom gates. So what do you do?
But it doesn't, yeah, so there are trade-offs that are being made here, but the idea is that you can trade off efficiency for compatibility, right? Like I can still potentially make it syntactically work, but it may not be the most efficient. Like I can synthesize R1CS into there, but obviously I'm not leveraging the full Planck universe of it because I'm just using like A times B equals to C.
Describing your circuits or your programs at a higher level also lets you, like the hashes that describe your programs can exist at a much higher abstraction level. So then if you I'd much rather fix a compiler bug and have a bunch of different bytecode hash changes than have the actual logic of the program change. So I think you want to code in as high level language as you possibly can, but then realistically probably run as low as you can.
I mean, it's scary. If you look through the Solidity compiler history, I mean, the Solidity compiler, all credit to they did a good job. I think it's a great team. The Solidity compiler had a lot of bugs, man, and zero knowledge just makes it harder.
All the haters, man.
Yeah.
No.
With Brian, what's one open question or challenge that you have, or question?
Yeah, the open questions I think we spend a lot of time on now is really thinking, well, okay, now we have ZK, so now what? And it really comes down to what does it look like to have parallel execution at scale that can act?
Is that not a solved problem and mostly a DevOps issue? When you generate...
No, I think it's like a state representation issue. It's like, do you have an account model? Do you use UTXO?
Even if you have an account model, you can do parallelization. There's also this kind of fallacy that people think that because you have account model, you cannot do parallelism.
No, you definitely can, yeah.
Yeah, so I wonder what's the... I guess in my mind, when you generate a proof, you run the execution, it produces some witness elements, and you fit these witness elements in the prover, and the prover then, you can parallelize it as much as you want. And you can also parallelize the witness element generation from running it. So I wonder, where do you see the bottlenecks there?
Yeah, no, I think I'm more talking about the application level model for what do developers actually interact with on a blockchain, and what does it look like to make a computing framework that's effectively blockchain compatible that is developer friendly at the same time. So actually making something that is, people love Solidity because it's easy to program, but the notion that you're going to have this ordered list of transactions is kind of built into the way all of this stuff works. So what does it really look like to have applications that are easily developable, that are very compatible with with being rolled up everywhere, I guess?
I for sure love Solidity. David?
Yeah, I guess I can give you maybe two. The first one, I'm very interested in people actually writing circuits, and I guess there are two problems here. There's the VM world and writing circuits without a VM, and in both worlds, you get different type of bugs. And I think in one of these worlds, you may have even very different types of bugs, and it's going to be very interesting to see. So for example, you can forget to create a constraint, or you can create a hint, so you compute something, and you forget to constrain it. Okay, so very interesting in that. The second thing is smart contracts that can hold a private key. And so if we mix, I guess I talked about that earlier, but I think that's going to be that's something that people have always wondered. It's can I create a smart contract on Ethereum, and when I create a transaction and I call that function in that smart contract, then the smart contract will sign a Bitcoin transaction, or will decrypt that message, or will generate some random value. And I think with ZK and MPC, we can probably try to do something like that, but yeah.
So my answer a year or two ago would have been, focus on the hardware acceleration, because we're going to need orders of magnitude improvement over CPUs to get the performance that we want. And today, I'd say please don't start a new hardware acceleration company, because there's now over 10 of them. Instead, just join one of the existing teams, many of which are in stealth. So just come to me and I'll point you to the right direction.
Or me.
I guess one kind of topic which is interesting to me and is kind of at the frontier of cryptography in terms of applied cryptography is witness encryption. So it allows you to do cool things like build a trustless, collateral-free bridge, two-way bridge between Bitcoin and Ethereum.
How?
Okay,
In a minute.
So the idea is very simple: is you generate a private key and then you encrypt it, where the witness is basically a proof of burn on Ethereum. So the process of locking, does that make sense? Yeah.
To me, but
So you have this public key which is encrypted. You send 1 Bitcoin to it. Now this Bitcoin is kind of locked on Bitcoin. And so what you can do is you can safely mint an equivalent on Ethereum. Now, in order to go back in the other direction, you basically need to burn the wrapped Bitcoin, as it were, on Ethereum, and then generate a snark that it has been burnt, and then the witness, the snark, allows you to get the private key and spend the Bitcoin back on the Bitcoin side of things.
you encrypt to a yet-to-be generated snark.
Yeah, you decrypt.
You encrypt, you spend to a public key, where the secret key to that public key is not known ahead of time. It's only going to be known after a burn of that Bitcoin that was minted initially is generated, and you make a snark over it.
Exactly, and it's like this. So when you look at what's theoretically possible, there's like obfuscation, which is like clearly like moon math, and like the thing about witness encryption is that it feels like it's just around the corner. We just need 1 or 2 more breakthroughs to make it practical, and it's surprisingly powerful in the sense that it feels much less powerful than obfuscation, but it turns out that many problems that can be solved with obfuscation can actually also be solved with simply just witness encryption.
Perpetually 18 months away. Okay, we should take 1 or 2 or 3 questions from the group, and thank you everyone for the conversation. Anyone? We can do it in a bit, but if anyone has any questions, please go for it.
Yeah, so I have one question. So
And if you want, direct it to someone from the group.
yeah, probably Justin. Yeah, so we all know like there are a bunch of teams working on the ZK VM or ZK EVM stuff, right? So right now, based on the current implementation, the hardware acceleration, as you mentioned, right? What's the like theoretical throughput we can achieve right now?
I mean, this is one of the benefits of the compiler-based approach, is that the performance is just so much better, and so I don't know exactly, but I mean some teams are maybe claiming tens of transactions, hundreds of transactions per second. Oftentimes they might be using GPU acceleration as the way to get such performance. Unfortunately, like teams like Scroll right now, they're just way too slow. So it might take a whole day to prove like 1 Ethereum block. And so here, hardware acceleration is not just a luxury; it's like definitely necessary. It's required, yeah. But the interesting thing is that there's kind of this equivalent of Moore's law for zero-knowledge proofs, right? And like the technology has definitely improved more than 2x every 2 years. I don't know how to quantify it, but I expect this exponential trend to continue for a few years. And we'll get to a point maybe in a decade where this stuff is just fully commoditized.
Yeah, thank you.
Either everybody understood it or nobody understood it. Oh, we have one. Okay, great.
Well, I have a question. Maybe David can answer this. If you're trying to maintain, say, just a Merkle root on chain of some larger piece of state, this might include the set of all spent notes in some kind of ZK system or some arbitrary contract state. And I download this state off chain, I do some kind of update, I produce a ZK proof that my update is correct. But in order to download this state off chain, I kind of need the whole Merkle tree, or more accurately, I need a path from the root down to the leaves that I care about. And of course, that requires that someone out there is remembering the whole Merkle tree every time it updates, doesn't it?
Yeah, so I guess you're alluding to what I was talking earlier, as to where the data is. So in this case, so if it's a rollup, you only have like maybe some sort of centralized service or whatever, and so they will keep that in memory. They will make backups or like whatever. Or if you go the Celestia route, basically you're keeping also like a version of your Merkle tree in memory, but you're preserving enough data on that data layer, I guess, to be able to reconstruct the Merkle tree. So you're pretty much it's kind of like a blockchain. You're adding all of the transactions there, and so you can reconstruct the states by just going through the entire history. Yeah. Or you store it on IPFS, or like there's different ways to.
Fair enough.
Sweet. Thank you all. Thank you to the group.
Thank you.
Thank you.
Thanks.
All right. Thank you very much for joining us today. Just want to say that the after party starts now. Make sure you grab the cocktails there before they close. And I would like to give a shout out to Maven11, who is giving us all those drinks.